IIT Gandhinagar. So Orpon, then it's over to you, and start in one minute or so, whenever you think it's appropriate.
Yes, I think we can wait 1 minute. Okay, let's start then. So let's start. So let's start the second session of day 5, and our first speaker is Tadashi Takayanagi from Yukawa Institute of Theoretical Physics, Kyoto University, and he will talk about ADS, BCFT, entanglement wedges, and wedge holography. So welcome, Tadashi, and now over to you to start that off.
Thank you very much. I'd like to thank organizers for inviting me to this really wonderful conference of dual mysteries of gauge theories and gravity in honor of David Gross. And in this talk, I'd like to give an overview of the subject is related to ADS, BCFT, and entanglement wedges. And finally, we'd like to introduce our recent work on some co-dimension 2 holography, which we call wedge holography. And this work is based on many collaborators, and especially I'd like to thank recent collaborators, Ibrahim Akar and Yuya Kusuki, and Yuki Suzuki, and Koji Umemoto, and Jisho Wei. All of them are at the YITP. So let me start. So let me start with the introduction. And as in many talks, ADS-CFT provides us a very great tool to understand gravity from the viewpoint of conformal field theory. But still, ADS-CFT correspondence is still in black box. In that sense, we don't know the basic mechanism. So we want to understand basic structure of this ADS-CFT correspondence. And one basic question is the following one. So which region in CFT is dual to which region in ADS? This is so-called sub-region dualities. And I'd like to explain two different sub-region duality. And the most standard one is so-called entanglement wedges. And this is basically the correspondence between reduced density matrix, so which captures information included in this particular region. And I will explain more later. Another one is ADS-BCFT, which is namely the holographic dual of conformal field theory, which lives on a manifold with boundaries. In this case, really we focus on conformal field theory lives on some part of the space and talk about its gravity dual. And the main aim of this talk is to explore some useful interplay between these two different ideas of sub-region dualities. And let's start with how they look like and a basic review of them. So let me start with the entanglement wedges, but before I'd like to explain holographic calculation of entanglement entropy. So in entanglement entropy in conformal field theory is defined in this way. So we have some quantum state, which is we write low tot, and we trace out some particular region called B, and we pick up density matrix for this limited to region A. This is called reduced density matrix and compute von Neumann entropy, rho log rho. So this is an entanglement entropy, but this by using ADS-CFT, we can calculate in a geometrical way by using this formula. So we just basic idea is we have CFT as a boundary, and we have some bulk, which is the ADS. And this is holographic creation, and we talk about some sub-region A, right? We decompose Hilbert space in CFT into A and B. And this separation is characterized by this boundary of A, the same as boundary of B. This is a very important geometrical object, and we extend this boundary towards the bulk. This surface is called gamma A. And we especially look at the minimal surface, but in more general Lorentzian setup, we first need to extremalize surface. We pick up extremal surface by taking variation about area function. And if there are several candidates, we have to minimize over them. But basically, so that way we get some kind of extremal surface, and which we call gamma A. And this area of gamma A divided by 4d Newton, like Bekenstein-Hawking formula, gives entanglement wedge. And the region inside this gamma A is called entanglement wedge. That's the main point of this part of the topic. I'll come back to this later. And so now, but before we go on, I'd like to just briefly introduce our recent progress about some generalization of holographic entanglement entropy. So these are, we can apply this formula for Lorentzian time-dependent background, also of course including static spacetime. But in some cases, sometimes when we, for example, talk about tunneling effect and also inner product, we encounter some Euclidean path integral. This is the usual method to calculate also entanglement entropy. And it is quite natural to ask what happens if we talk about Euclidean time-dependent background. And in this case, we can nicely define minimal surface, and it is quite natural to ask what's the CFT interpretation of this minimal area surface. And we find, our recent work, we find that actually this area, minimal area, is not equal to entanglement entropy, but more generalized quantity, which we call pursued entropy. Pursued entropy is defined this way. This looks like von Neumann entropy, but this tau A now depends on two different states because we are talking time-dependent, Euclidean time-dependent background, which we have to specify initial state and final state. Right? At t goes to infinity and t minus infinity, we have initial state, and later we get the final state, and we pick up some middle minimal surface. And this area computes this pursued entropy and defined by this transition matrix. Transition matrix is kind of combining initial state and final state, trace out some region. Right? And then we can easily derive this formula by using the replicatoric and as in the Lukovic-Maldacena derivation of the standard holographic entanglement. But anyway, so here I would like to talk about entanglement wedges. And this is, again, this is a question that which bulk region is dual to a given region A in conformal theory, and answer is called entanglement wedge. So if we talk about this area spacetime and restrict it to some region A, this is a CFT, lives on the boundary, and some particular region on the boundary is called A. And information of A is characterized as a reduced density matrix rho A in conformal theory, and this is dual to this red region. This is called entanglement wedge, MA. And so this reduced density matrix for this region in the bulk gravity is correspond to this rho A in the CFT. This is the idea of entanglement wedge. And so if we look in a full Lorentzian picture, it's a really wedge, right? So we have some region A and minimal surface gamma A. In the surrounded region is this yellow region, but this we extend in this kind of light cone, right? Domain of dependence. This is the actual definition of entanglement, but we are mainly talking about static spacetime. So in that case, we can restrict to this time size. Okay. And the characteristic feature of this entanglement wedge is the behavior of so-called phase transition. And the entanglement wedge, so if we talk about the entanglement for disconnected subregion, A and B, they are disconnected. And if A and B are relatively separated and their size is small, then minimal surface also disconnected for computation of entanglement entropy for SAB. And in that case, entanglement wedge also disconnected. But if A and B gets closer, right? If they are close, then minimal surface connects them, and then the entanglement wedge is also this connected region, this red region. And in this case, mutual information is positive. So there are such a phase transition behavior. This is quite characteristic for the behavior of this entanglement wedge. Okay, so then we go to next subregion duality, namely ADS BCFT correspondence. So in this case, we talk about the boundary conformal theory, BCFT. And for boundary, BCFT is defined as follows. So for special choice of boundary conditions, a part of conformal symmetries are preserved. And this is called boundary conformal theory. We just write BCFT. And in terms of symmetry, so CFT D plus one dimensional CFT have a SO2D symmetry. And B, if we put some boundaries, so this is a D plus one dimensional conformal theory, and we put the boundaries, this breaks roughly half of the conformal symmetry and half of them is kept preserved. So that remained conformal symmetry, boundary conformal symmetry is SO2 comma D minus one. So if we have this symmetry, so we call this boundary conformal theory. And the point is that, of course, we have to specify some boundary condition. So we label boundary condition by alpha. This I will write this way. And in two-dimensional conformal theory, so the one-dimensional boundary, in that case, often people introduce some idea of called boundary state or Cardi state, which satisfy this Virasoro symmetry. And so we write it to be alpha, and alpha is state still meets levels of these boundary conditions. And if we have an endpoint function on disk or upper half plane, we can write this way. Right? We have this vacuum, but we insert one boundary, and this is a boundary state. So this is the definition of boundary state and boundary conformal future. Okay, and then so this is the field theory definition of BCFT, but we have some simple geometrical way to construct its gravity dual. So this is the ADS BCFT. And so this is a heuristic picture of that, but this essentially captures everything of this ADS BCFT. So we have some region A, right? We're talking about the conformal theory lives on A, but with a boundary, partial A, boundary A. Right? This is just CFT, and we extend, as usual in holography, extended in the bulk. And this boundary of A is extended to some surface which is called Q, and this is a new surface in the bulk. So originally, we don't have a boundary in ADS CFT, so this is a whole region is the ADS space-time, but we cut ADS space into two parts, and outside and inside of the surface, and now that this surface is called end of the world brane. And here we impose this Neumann boundary condition. KIAB is the extrinsic curvature, and TAB is some boundary energy stress tensor localized on Q. So claim is that this CFT lives on this A, BCFT is equivalent to gravity lives on this manifold M, which is surrounded by this end of the world brane and this boundary A. And why we impose this Neumann boundary condition is just also analogous to Randall-Sandler model, but we want to keep binary dynamical, and there are no reason to specify particular metric on this Q because this boundary is dynamical. And you can see, for example, particular example of string theory like Orient fault gives exactly this condition, much simpler. This KAB is just 0 by Z2 invariance, Z2 orbifold invariance, and we can also construct this kind of model in string theory. Okay, so this is the ADS BCFT. And now I'd like to also emphasize the difference between these two sub-region duality. First one was this entanglement wedge. The picture is the same, right? It looks very similar. Surrounded by minimal surface, surrounded by extremal surface, but the extremal surface is mathematically written in this way. Right? Trace part of extrinsic curvature is 0. But then on the other hand, in ABS BCFT, this Q is a really dynamical brane. End of the world, which is the end of the world brane, which is a dynamical brane. It has a tension. We can put also tension on this brane. And in that case, this Q back react geometry. So in that case, KAB, full component of extrinsic curvature is fixed. So that way, this is so different. In this first one, we don't need to take into account back reactions. We can just keep the same background and just calculate extremal surface area. That is an entanglement wedge and entanglement entropy. But in ADS BCFT, we have to, in general, take into account back reaction. But we want to, in this talk, we will see the very interesting connection between them, especially we are considering entanglement wedges in the context of this ADS BCFT correspondence. So this is a simple introduction, and I'd like to go to the main topic of this talk. And first, we give some review of this ADS BCFT and computation of entanglement entropy and structure of entanglement wedges, which is very interesting, recent application also. And then we go to the entanglement. We want to derive entanglement wedge just purely starting from conformal field theory. And we apply this idea to ADS BCFT. And in ADS BCFT, we have a very special feature of entanglement entropy, so entanglement entropy and also entanglement wedges, where we have some extra pieces, which is called island. Now, this plays a very important role to understand this black hole information, but that structure is obvious now in ADS BCFT. And finally, we'd like to introduce our recent progress about codimension 2 holography. Okay, so now let me talk about this ADS BCFT and calculation of entanglement entropy. And this basic example of ADS BCFT is the just simple choice of this boundary energy stress tensor, TAB, localized on this end of the world brane Q. And then we just introduce tension, T, and so TABQ is proportional to tension, and HAB, just induced metric quantity. And this case, this equation motion, Neumann boundary condition takes a very simple form. KAB is just proportional to HAB, and we can solve this precisely. And then we talk about gravity action on this background of this M, like gravity dual of this BCFT, just take a standard form, Einstein-Hilbert action, and Gibbons-Hawking term plus tension term. So then we can explicitly construct gravity dual by looking at some metric. And the most simplest one is this setup where CFT lives on the upper half plane, right? Boundary is just straight line and the left-hand side is just for BCFT. I will talk about this W direction, this is the X direction. And this case, its gravity dual is depicted in the right picture. So we have like this CFT lives on this semi-infinite line, or this half space, half plane. And this boundary is this map to this boundary, but we have this extra dimension, right, Z direction. So we have extend this boundary towards the bar, right? This is surface Q. But in this example, at the ground state, everything we can write in the ADS language, ADS metric, and this is kind of hyperbolic slice, ADS slice of ADS space. D plus 1 dimensional Untitled Chapter space is written in terms of slices of this ADS, D dimensional ADS. This manifests this boundary conformal field symmetry. Totally, this is Poincare metric, but we can write this way, and this ADS D metric also again 1 dimension smaller Poincare metric. And that way, this surface Q is in this context just ADS, lower dimensional ADS space. And this low is the most important direction, is just this radial direction, which is starting from the boundary of A boundary and goes to this end of the world plane, right? That this way. And the low takes minus infinity here, and the 0 and the low star. Low star is a parameter and related to tension of the through this boundary condition. If the tension is large, then large degree of freedom, so we have larger space. Gravity dual gets larger, and so on. Okay, so this is a gravity dual, and this now we come to this holographic entanglement entropy, and this calculation is we can use this similar minimal formula, minimal and extremal surface, and extremalizing and minimal minimization, but actually we have one more ingredient. So one more ingredient is, so we have some surface, we have some region M, which, so we have this is a BCFT lives on here, and we talk about subsystem A, and this is 1 dimension higher, this holographic space, gravity dual, and we're talking about, right? So this is a BCFT, and we're talking about entanglement entropy for region A, right, with boundary. So this is dual to this holographic picture, left-hand side. And to calculate, we need a minimal surface, gamma A, extremal surface, gamma A, but it can end on the surface Q, right? This is the end of the world plane. We can end on this gamma A on this Q. So this is a new ingredient, and this makes some particular extra region called B, and this is nowadays known as island. It's applied to graph information problems, but we can end on this B, and we have to minimize also not only gamma A, but also the location of B and shape of B. And this is a holographic entanglement entropy in ADS BCFT correspondence. And then, so we can think of a particular example. Simplest example is ADS3 and BCFT2. And there, the entanglement entropy is related to very important quantity called boundary entropy, which is kind of analog of central charge in 2-dimensional conformal field. So we are talking about 2-dimensional conformal field with boundary, and boundary is labeled by alpha. And as we mentioned, and this we're talking about some boundary and described by boundary state. This is called Cardi state, and this is a disk amplitude written in terms of endpoint function inserted this boundary state right here. And it's boundary entropy, so it's defined. Just next slide, but the boundary entropy is a nice measure of degree of freedom localized as a boundary introduced by Affleck and Ludwig. And there's a nice theorem analogous to C theorem, which is called G theorem, and boundary entropy decreases under the boundary RG flow. So we keep this bulk is conformal invariant, but we can break conformal invariance as a boundary by putting relevant boundary perturbation, and then this quantity called G is monotonically decreasing. And then here is the definition of boundary entropy, and I give some 3 different definitions. First one is boundary entropy is just a disk amplitude. But we have to be careful about normalization of this. This is a whole point, right? Normalization of disk amplitude. That is fixed by the cylinder amplitude. We can talk about cylinder amplitude, which connect to different boundaries. This is maybe you can look also D Branes, alpha and beta in string theory context. And then we can naturally determine the normalization by looking at the open-closed duality or Cardi's condition. And if we take L goes to right, if the alpha and beta is a far apart, boundary is a far apart, then it factorizes in this way. So disk amplitude alpha, disk amplitude beta, and some bulk contribution, which is proportional to L. Right? And as we can extract some boundary entropy because this is defined by disk amplitude. And finally, so we can define also looking at the entanglement entropy. So the entanglement entropy in the presence of the boundary as worked out this Calabrese and Cardi. So we have some time slice and subregion A is here, region A is here, and the length is L. Then it takes this universal formula, right? This is a bulk contribution. This is half of standard formula, right? For the Larsen-Wilczek formula is C over 3, but this is we have boundary, so we cut it into half. So its contribution is half, but we have an extra piece, right? Constant contribution, which is precisely same as this boundary entropy. Okay, so now we go to this calculation boundary entropy from holographic side. So for that, so actually, so we want to relate this to disk amplitude. So we want to have some disk. So we explain this very simplest setup that this boundary of A is just straight line. Right? This is a BCFT upper half plane. BCFT is in the upper half plane, but we can act some basic conformal transformation, global conformal transformation, namely special conformal transformation, and this is a bulk counterpart. This is a bulk ADS counterpart, and this is just dual to straight line in the bulk, and this is mapped to actually round sphere, right? This boundary goes to a circle, and the region A is mapped to disk, but this full bulk, this bulk surface end of the world plane mapped to this part of the sphere, right? Given by this obvious formula. So this is by using this formulation, so we can just calculate, gravity action in this region, and so that gives a final result of this boundary entry. Right? We evaluate this Euclidean action, and it's divergent. Right? We have epsilon is a UV divergent in the just z equal epsilon, right? Cutoff, and we have divergence, but we pick up, right? We do some holographic normalization and pick up constant part, and that gives rho star divided by 4g Newton. And rho star was this, right? This angle, basically this angle over, right? We write it here. Here, rho star is this, right? Location of the surface Q. And that way we can have the rho star divided by 4 Newton, very simple formula for a boundary entropy in holographic calculation. And we can rely this in terms of tension. R is a radius, T is a tension. When it gets larger, then boundary entropy also gets larger. And finally, so we go back to another, right, this third definition of this boundary entropy from holographic entanglement entropy. Here, the previous restriction plays a very important role, right? So we have some region A here. This is a straight line. Now we don't need any disk like topology, but we just talk about half plane. And this is a time. You can think this is a Euclidean time. Tau is a Euclidean time, and we talk about some region A here. And we talk about entanglement entropy, and this endpoint is important. We extend this, right, the endpoint towards the bulk, and this makes some extremal surface gamma A. But next we have to minimize this, right? There are many different geodesics which end on the surface Q, but because it depends on the endpoints, right? We change endpoints and minimize area, minimize length, and that precisely means that this is just simple circle. This length is the same as A. So this gives an answer, right? And this calculation, and finally we get exactly the same formula, like as here. So this is consistency check, and we can calculate this boundary entropy from holographic entanglement entropy. Okay, and yeah, and I want to make one more remark that actually, so we can also derive G theorem, a holographic way. And for this, we can just impose narrow energy condition. I'm not going to details, but in the end, I'm imposing this narrow energy condition, as is also true for C theorem, holographic C theorem. We can show this quantity G, this is a kind of analog of G function, defined by just basically angle of this X and Z. This quantity basically monotonically decreasing. This quantity. So this quantity basically measures the angle, right, of this, how this end of the world will be tilted, and the angle should decrease under RG flow. This basically this formula tells us. So it's go this way, right? But this dotted line is not allowed. This is prohibited. This opposite going, kind of accelerating trajectory is kind of prohibited. But this guy is favored, and that actually manifestly shows if we talk about static spacetime, then there are no wormholes, traversable wormhole we can create this way, right? So this kind of mending is not allowed. It's always go the opposite way. So this is sort of topological censorship when in the presence of boundary. So without boundary, we know, right? Topological censorship, it is related to causality in ADS-CFT correspondence, but we have some analog of that in the presence of boundary in ADS-BCFT correspondence. Okay, and this is a story of this ADS-BCFT, and I'd like to now go to entanglement wedges. And finally, we combine these two. But so here I'd like to give, based on our recent work, we'd like to give just CFT derivation of entanglement wedges. Usually entanglement wedges is understood in the presence using ADS-CFT and some bit of some calculation CFT, but here we just purely derive entanglement wedge from CFT viewpoints. So our setup is very simple. So we are talking about the locally excited state. This is a probe, actually operator is probe. So we talk about some operator excitation, local operator excitation O, right? We put some primary. And location is important. We call it W. It's a primary 2D CFT and conformal dimension H. We put some excitation and we're talking about some subsystem A and tracing out the other region B and talking about this reduced density matrix rho A. And the point is that the reduced density matrix depends on the location of this excitation, W. This argument is very, very important. We are talking about W dependence of rho A. This is our target. And then, so the reason why we're looking at this is motivated by ADS-CFT, of course. And so we can talk about the gravity dual of this reduced density matrix. So we are talking about some excitation, right? And if we excite this point, and this is a Branes state and keto state, and another point in keto state, like here. And so we can talk about this trace of this guy. That is a 2-point function, right? That basically the length of this geodesic line. So if we excite this 2 point, along this geodesic, we have bulk excitation. This region, this blue curve is excited in the bulk. And let's focus on time slice, then it passes through some particular region, point P. If P is inside entanglement wedge, we know, right? This reduced density matrix rho A knows this point. We can distinguish two different points if W is slightly shifted. But if this point P is outside, right? If O is much further, then this point P is outside of entanglement wedge. Reduced density matrix rho A cannot probe the location of W prime. So even if we excite this point or a little bit different point, this rho A we cannot distinguish from rho A. Rho A cannot distinguish. And for this, we assume this conformal dimension is much larger than 1 because we assume some geodesic approximation, but much smaller than C because we want to keep the metric of ADS, pure ADS spacetime. We want to neglect back reactions. So we want to see this rho A may be sensitive to only rho OW, but not W prime. And by looking at this location, we can distinguish these two and we can identify this entanglement wedge location. So for this, to see that distinguishability, we are using information metric. So rho A is sensitive to OW, operator W, which is we can distinguish these two guys, right? When W and W prime is not the same. So to see this distinguishability of quantum state, consider the Branes distance between this density matrices, rho and rho prime. And Branes distance introduced this way. So it's like if this rho and rho prime is the same, this part is just 0. This is like inner product. And so this distance goes to 0, right? If rho and rho prime is the same. And the whole pure state, it's just simply inner product indeed. But this is good thing is this, we can apply this for mixed state, right? Rho and rho prime is a reduced density matrix. We can extract distinguishability by looking at this Branes distance. Okay, and so we talk about this family of density matrix, and then we introduce this metric, right? By this way, by looking at this distance, but slightly this, we assume some density matrix is parameterized by lambda, and so we slightly change the value of lambda, and this, we see the response. Right? Always it started quadratic order, and the Z is how measures how this density matrix changes if we change the parameter, and that way we get information metric. Right? If we talk about this single excitation of just this pure state, then we get nice, very simple Branes metric after calculation of 2-point function, which is universal. We get just this very simple result. And this precisely agree with the time slice metric of ADS3. So this is nice, but actually this is too good. right? Because this is intuitively clear because we talk about the distinguishability of two excitation, but this is basically same as distinguishability in the bulk of these 2 points, and namely just distance between these 2 points in the bulk ADS. So this is quite nicely agree with ADS CFT, concept of ADS CFT, but this is too good because here we are talking about we can talk about any CFT, like 2-point function is universal in any CFT. So, but we expect only ADS3 classical geometry only emergent for strongly coupled CFT. So for this, actually, we need a more sensitive probe. Namely, we should look at some tracing out quantity like rho A. Right? We have to trace some part. Then we see the difference between weakly coupled theory and strongly coupled theory. So here we go. So if we talk about the single interval reduced density matrix, this simplest case, we are talking about some region here, right? And so we're talking about region A, and its length is L. And then we again talk about this reduced density matrix. And we can talk about distinguishability by looking at fidelity, but the fidelity is actually very difficult to calculate. We will do later, but not going to detail, but we can do this. But before that, it is easy to see some more easy quantity, which is kind of Rényi entropy versus von Neumann entropy. We are looking at Rényi version of fidelity given by I-rho prime. This is first introduced in Kari. And if this quantity is 1, this means rho and rho prime is the same, right? We cannot distinguish these two guys. They look same. But if this is smaller than 1, then we can distinguish these two. And this quantity, and because you have square of rho, and each rho has a 2 operator insertion, and this is totally, I-rho rho prime is totally given by a 4-point function. And we have a density matrix for W excitation, and another density matrix for excitation happens W prime, right? And we are changing W and W primes, and so that we can say some distinguishability about this quantity. And interestingly, we can see this emergence of sharp entanglement wedge as follows. So here we are talking about holographic CFT, and so if we talk about some region A, and this is actually this purple region is a kind of analog of entanglement. Indeed, just projection of entanglement wedge towards the boundary. I will come back to this later. And if this excitation, two excitation outside, then always we get I equal 1. We cannot distinguish 2 points, 2 excitations. On the other hand, if these two guys are inside the same wedge, this entanglement, sort of entanglement wedge, then we can distinguish. Even when this W and W prime is a little bit different, then we immediately see this no overlap. So this manifestly shows this presence of entanglement wedge, but this is actually come from the simple calculation of holographic CFT. We have rho and excited W, and this point is excited rho prime. And we are talking about this replicated geometry. We're computing trace rho prime after conformal mapping, and we get into the single seat, and we just talk about, just compare the lengths between this length and this length, right? This length is trivial contraction, right? This D1, D2 come from this guy. But the non-trivial guy is this guy, and this point and the other point, right? Other point. So across the seat. And these two guys are compete, and if non-trivial guys favor, then immediately we see this I-rho prime is non-zero, non-trivial, not just 1. But if trivial one is favored, then we get the trivial result. And you can see, right, this green guy is obviously trivial one is favored because distance is shorter, right? Trivial distance is shorter. But this case, trivial distance, G1, D2 is larger, right? The non-trivial one is favored. That way, we have a very simple phase transition-like behavior. And we see that if we excite this point inside this shaded region, red shaded region, this is actually just boundary counterpart of entanglement. We just, along this geodesic, we project this entanglement wedge towards the boundary. And inside here, we can distinguish 2 points, but outside we cannot. So that this manifestly shows the location of entanglement wedge. This is a shadow of entanglement. Okay, so we can actually give some numerical plots for this more precisely. So we can compare also holographic CFT versus free scalar CFT. In holographic CFT, so we can have this result. Let me explain the setup. So we have some subsystem A's here, and this is a CFT wedge. This is a kind of shadow of entanglement wedge. So if let's assume 1 point is inside, then outside we prepare another point here, and then outside here, if this point is here, it's right. This overlap is 0, right? We plot I-rho prime, right? This guy. because this point on the outside is different, right? It's just 0. But when this point gets very close to this excited point, it's going to just 1, right? They say this point, these two stay the same as we expect. This behavior is very common to both cases. Even free scalar and both strongly coupled CFT, we get the same result. And if we assume the other initial point is outside, then anyway, we are looking at this reduced matrix A, even though the other one more point is gets closer to this point, right? We cannot distinguish two guys, right? Always, even if this point or this point, it's just 1, right? They say these 2 points are not distinguishable, they're just same. But if we go, this point gets inside this wedge, it suddenly tells us that these 2 points are different, right? Because 1 point is they capture, right, in wedge. So we have some very simple, very sharp dip here, right? Cliff, very sharp cliff upwards. But if we look at the free scalar, everything is ambiguous, right? There are no sharp entanglement wedge. This very sharp structure shows that for holographic CFT, we have very sharp entanglement wedge. So this is quite, satisfied because it's agree with what we expect for entanglement. But anyway, so here, this is purely using CFT calculation, we derive this entanglement wedge. We don't rely anything about the CFT here. And we can also, this is actually calculation of I rho prime, which is not satisfactory measure. It's a kind of a Laney version of fidelity, but we can look at the actual fidelity by sort of using some kind of really complicated double replica method. We start rho m, rho prime to the m, and we take n's power, and take n and m goes to 1/2 limit, and we can get reproduce basically what we expect. Again, essentially same result as here. And we can also, in this case, extract some Branes metrics, precisely gives again this hyperbolic metric, and same as this previous pure state, and agree with entanglement wedge geometry. Okay, so and we can go to a little bit more complicated case, but non-trivial case where we have a nice phase transition I introduced in the beginning. So this is a double interval case, and we can talk about this, again, 2D CFT and infinite line, and we talk about two subsystems A1 and A2, right? And we are talking about this I rho prime, and also we can do fidelity. And if we do some I rho prime, actually, so what in summary, what we find is here, right? So we have some, this is an extra dimension, but actually here we are talking 2D CFT. This is just a Euclidean time direction. And what we expect is green curve, right? Green curve is just the ADS CFT prediction, the entanglement wedge of ADS CFT, right? Minimal surface. But what we get from this red guy, this Laney version of distinguishability measure, this is not exactly good distinguishability measure, and indeed there's a small deviation. This deviation doesn't happen in this single interval case, but only happens in double interval case, complicated case, and but very small actually. But anyway, this kind of topology is same, and only small deviations can be seen for this measure, first measure. But if we look at genuine fidelity, they're precisely same. We can see this green curve. This green curve is come from ADS-CFT, but also agree with fidelity calculation. So here is some numerical plot for this red guy. So this is a red. This yellow curve is actual entanglement wedge, and it also agree with fidelity calculation. But this blue guy is very small. You cannot see in the first picture, right? And if we just magnify here, we see some small difference. It's just 1% or 2% difference. And we see this the blue guy is this I rho prime, which is a kind of Laney version of distinguishability measure. So it's not so good measure, so it's a little bit deviated. Okay, so these are story in the case of this, standard ADS-CFT, and it's their entanglement wedge. And I would like to talk about entanglement and wedge for ADS BCFT, boundary conformal theory case. We can do similar trick of distinguishability calculation by using BCFT. Now we put some boundary state. We put some boundary. Here is our density matrix. So we excite these 2 points, right? We point and we look at the dependence on W, but now we also have to insert the boundary. We have boundary here. Let's talk about this simple setup. This is very usual, very useful setup for quantum quenches and also black hole, single-sided black hole construction. And then we have W1, W2, and rho and rho prime. And we W1 and W3 is a different point. We excite different point. And we do some conformal mapping. And we in the end get some this kind of cylindrical picture and just single seat. And using some kind of elliptic map. I'm not going to details. But anyway, for this calculation, there are three possibilities. This trivial contraction. Rho prime is again 4-point function. So we have two different weak contraction in holograph CFT. Is a trivial contraction and this non-trivial guy across the seat, and finally boundary contraction. But we neglect this boundary contraction because even from the beginning, if this happens, then we cannot prove the geometry even for pure state. So we just neglect this, and we can just fine-tune particular good operator where there are no boundary contraction. And that's possible. And so this is our assumption. And then here is the results. So we talk the expected entanglement to H in ADS BCFT is like this. This is a boundary, ADS boundary, and this is a black hole horizon. So this background is dual to for a single-sided black hole geometry, like this Hartmann and Maldacena. And this is a black hole horizon, and this is a time slice, and this is a region A, right? It's a minimal surface like here. But if the size of region A gets larger, then actually minimal surface end on the horizon, because this is a kind of end of the world brane. This is exactly the same as its ADS BCFT construction of this end of the world brane. So this is kind of analog islands in the story. And so there are phase transition, and indeed we can see this phase transition in our calculation of this I-rho prime. This is a blue line, and again small deviation of this Rayleigh measure and this actual ADS CFT entanglement wedge expectation. This yellow guy is ADS CFT, and the blue guy is this Rayleigh-like measure. But it's precisely, and we have some this phase transition if we increase the size of A precisely, and we have this sharp boundary here, and this overlapped region is an entanglement wedge computed from this I-rho prime. And we neglect this green guy because this comes from this third contraction. Let's neglect this, then precisely agree with what we expect from ADS BCFT construction. So in this way, we can confirm the entanglement wedge for boundary conformal field theory and this holographic dual by using just field theory calculation. So in this way, we confirm this picture, right? So we have some region A, and this end of the world brane. It's really this minimal surface can end on that, and we have to minimize over this location. We only see some particular simple example, but that's characterized basic issue. We can also do some conformal mapping of this result and get which covers many different results. Okay, so to connect, for example, this island story, we need to use some brane world holography. And the brane world holography is like we cut some ADS spacetime in the middle, finite cutoff. We cut out some region. This is just Poincare radius, and we just cut the equal A and impose, instead of Dirichlet boundary condition, we impose Neumann boundary condition even for ADS boundary. And this is a bundle Sandov setup. And then, so we can do some Karzak line reduction on this Z direction, because Z direction is warp direction, is essentially this gravity becomes one dimension lower. And we can extract some lower dimensional Newton constant by Karzak line reduction. And brane world holography tells us that classical gravity on ADS T plus one dimension with Neumann boundary condition with imposed as a boundary is equivalent to some sort of quantum gravity which lives on the boundary, right? D dimension, and coupled to large N CFTs. This is a brane world holography. And so if you look at the holographic entanglement entropy in this setup, this is a holographic entanglement entropy, but we can rely, we can expand by cutoff, right? Cutoff A in this setup. And so the leading term is area row divergence. But actually this combination, this cutoff and the D plus one dimension Newton constant, actually using this formula, we can rely this one dimension lower Newton constant. This is just, now we have entanglement entropy here is the same as gravitational entropy in this lower dimensional gravity. Okay? So this is a kind of consistency condition. In other words, this means lower dimensional Newton constant emerges by kind of matter, that this is kind of induced gravity. This is quite usual, usually happen in this brane world setup. And we can relate this also have a like this paper, we can relate this to black hole entropy. So we can talk about brane-wide black hole entropy is related to entanglement and holographic entanglement entropy in the bulk. Then anyway, so we can apply this brane-wide holography, and we get this equivalence of these three different pictures like this. First one is just boundary conformal field theory. And as we already explained, we have ADS BCFT. This is related to this setup, right? M, region M, and this end of the world brane, and the surrounded region is untitled space. But we can also talk about this brane-wide holography from here to here, right? So we can talk about brane-wide holography so that Q is now in the bulk, right? It's much like this surface. And then this means somehow bulk theory is dual to this, lower dimensional gravity, right? But also, of course, we have a regular boundary there, so these two guys are coupled. But also, again, we can go back to the original one because this gravity lives on this anti-Doshita space, D-dimensional anti-Doshita space. So we can go back to the bound. I mean, you can use ADS-CFT again and shrink this size to one dimension lower. D goes to D-1, which is namely this BCFT boundary, right? So that way, we have these three different pictures. This is now that's called double holography. And by using this double holography, we can derive so-called island formula discussed by the authors. And it's like, this formula is essentially same as this, entanglement entropy, holographic entanglement entropy in ADS BCFT, because this setup, right? This is a kind of, we want to calculate, entanglement entropy of CFT coupled to gravity, right? This is a basically idea of island formula. But this situation is the same as this ADS BCFT. And then we know how to calculate it, right? As I explained, so we put some extra boundary B and just minimize the area, right? And this extra boundary, we have some gravity, so we pick up some also gravitational entropy when we put some additional Newton constant. And but anyway, so this point is that entanglement entropy, we have to minimize over this entanglement entropy A union, this island, namely this B. B and I island is the same. So this event gives this, owing to these wonderful results and also discussed by several talks in this conference, we have some nice understanding of page curve, which is important in black hole information product discussed by many. Okay. Okay, so as my final topic of this talk, this kind of continuation of this idea of this double holography and ADS BCFT, I'd like to explain our recent work on this codimension 2 holography. So this setup of this holography is which we call wedge holography. So this is very similar to ADS BCFT, but we cut also both sides. Right? ADS BCFT covers one of the boundary reaches of ADS boundary, but the other guy in the middle, right, in the bulk. But our case, this wedge holography, we take both of them in the middle in the bulk, right? So we are talking WD+1, this region. We are focused on gravity on this region and what this gravity dual to. And for regularization, we put some surface, a very tiny cutoff is equal to epsilon, and that gives some very small surface, but small boundary called sigma. But the main part is just boundary that's Q1 and Q2, which looks like lower dimensional anti-Doshita space, ADS-T. Right? And this W is a part of D+1 dimensional anti-Doshita space, and this metric is the same as previous one. We take some this kind of ADS slice, right, of ADS space, ADS like slice. And we rho is this direction, and rho is again this larger direction. Okay, and then let me first give our claim. So this, we are talking about the gravity on this limited in this region, actually dual to two-dimensional lower theory in the end. This D+1 dimensional gravity on the wedge is actually dual to D-1 dimensional conformal field theory, lives on this wedge. This is like codimension 2 holography. But one way to understand this, first we go to this D+1 dimensional gravity to, we have in mind some brane-wide type holography, go to one dimension lower gravity, quantum gravity, which lives on this boundary, Q1 and Q2. And then we can perform again this ADS-CFT and down to D-1 dimension. Then there are no gravity here. So this is one heuristic interpretation, but there are other interpretation, which is more clear in understanding by using ADS BCFT. So we can talk about this BCFT. We have two boundaries, right? We can talk about this two end of the world brane. This is the AES boundary, and this is Z is the extra dimension, right? This is extra dimension, and we have bulk. This is a boundary. And we can talk about some interval, right? This is a CFT defined on an interval with just W. And it's dual to, and this the endpoint is a boundary. Boundary are dual to Q1 and Q2. There are two boundaries. And this region is dual to this BCFT, but we can take a W goes to 0 limit, then the physical size of this width of this interval goes to 0. That means we start from D-dimensional BCFT, but goes to D-1 dimensional, some sort of quantum field theory, some quantum systems. And what is a, right? We want to understand what this quantum system looks like. Anyway, it looks like codimension 2, right? This D+1 and this shrinks 0 size means D-1. And so we can calculate, for example, entanglement entropy. This actually simply descends from, this comes from ADS BCFT calculation, right? We put this island region again. So we're talking about this, the region A is defined in this two-dimensional lower theory, this interval. And it's dual, and it's related to the surface in this codimension, in this kind of lower dimensional ADS CFT, and again increase one more dimension by another doubled holography. So in the end, actually, we talk about kind of codimension 2 holographic minimal area surfaces. Right, so we're talking about the region A, but first we extend the region A to this gamma A. End of the subsystem A is extended to the bulk Q1, Q2, but again one more extension in the really full bulk, right? W wedge region. So that way we need a two minimization. So this double minimization seems to give some holographic entanglement entropy for this this kind of setup, and we can calculate it. Anyway, now this answer is very simple. The simplest setup, then it's just a line, then this is just again just part of the regular round sphere. So then we can confirm this is really satisfy this double minimization and calculate it, and then we have area of time, and this is familiar looking formula, but it's different because we are talking about codimension 2 holography, and we have non-trivial integral, but this logarithmic coefficient precisely matches what we expect for conformal anomaly. Also, we will see this in lowest dimensional example. But this structure, odd dimensional case, looks like, F function, and even dimensional, we have logarithmic divergence. It's precisely agree with the structure of D-1 dimensional conformal theory. And in 2D CFT, we can calculate with also detailed coefficient. It's related to this low star, which is the tension also of this brane. And from this, we can compare this with well-known formula of this C/3, and we get a central charge given by low star. And actually, this is consistent with this 3D Newton constant, which realizes in this grain world holography I just briefly explained. And also we can combine this with Brown relation, also explain this central charge. But one more explanation of this central charge is just the evaluation partition function. So this is a partition function, this 3D geometry, 4D geometry, to this codimension 2 holography. And we calculate this wedge region, and we evaluate partition function, we get some logarithmic divergence like this. And we can pick up this coefficient, and we know this coefficient is just C/6, and Euler number, this is just 2, right? That means this is C/3, and that again, we get the same result, which also obtained from 2D CFT. And we can do the similar calculation for higher dimensional case, and we can extract correct conformal. So that way, we have some nice correspondence between this wedge, like a wedge region gravity is actually dual to a two-dimensional lower conformal field theory. So there are, of course, many things we can work out. And for example, we can look at the correlation function, and we can at least 2-point function. This works well, and we confirmed. And there are many future directions. Okay, so these are basically all of my talk, and let me summarize conclusions. In the initial part of this talk, we reviewed two different subregion duality, namely entanglement wedges and ADS BCFT. And we showed that entanglement wedges can be derived purely from CFT by using information metric, distinguishability measure. And this CFT method can also be derived we can derive this also from entanglement wedge in ADS BCFT, and that explains this recent island prescription via double holography argument. And also we take a limit, particular limit, zero size limit of ADS BCFT, we can derive some codimension to holography between D-1 dimensional CFT and this D+1 dimensional gravity, which lives on the wedge region, which is no longer asymptotically ADS. Or even though it's like part of ADS, but it's no longer asymptotically ADS gravity region. But in that context, holographic entanglement entropy is given by double minimization formula. And here is some future problems. And so ADS BCFT, it depends on, sensitively depends on the choice of tension. And so far in the Euclidean setup, we have to take tension to be smaller than 1 over r or D-1 over r. And if we go beyond this bound, there is a strict bound. And if we go beyond, for example, G function, right, boundary entropy becomes imaginary and there are many problems. But actually in Lorentzian setup, we can think about this outside region, but because this just gives space-like boundary, right? That is, of course, quite an exotic one. But if we admit this guy, actually we can construct such a boundary by taking some analytical continuation of regular boundary. For example, imaginary radius of this, imaginary radius this. And for example, this corresponds to in the ADS BCFT setup, it's just kind of floating sphere. So we somehow eliminate inside the sphere region in ADS. And this such a surface satisfies this outside condition, right? It's go beyond the bound. And if we have this kind of setup, we can have some bubble creation, new creation, and giving some new space-like boundary. This is quite interesting future problems. And it's good to work on more on this codimension 2 holography and string theory realization, RG flows and correlators. And finally, also it's quite interesting to extend ADS BCFT is more complicated system, like including some sort of hint of quantum gravity, like higher spin gravity and so on. Okay, thank you very much. I think I'll stop here.
So thanks, Tadashi, for wonderful talk. And we can now take questions. I think Owen have already asked a question. Owen, can you ask directly?
Hello, Tadashi.
Hello.
I want to ask something about BCFT, this BCFT proposal. So how do we know that the matter on this extra extension of the boundary is only a cosmological constant?
Good question. Actually, yeah, that's an excellent question. And actually, let me go to the slide. Yeah, here. So so in my talk, we assume this function, but you can put some scalar field or fermion field or gauge field here, actually, which localize on Q. The reason I neglected, we just want to focus on gravitational degree of freedom, and to calculate boundary entropy, actually tension term is enough. And another reason, I want to keep conformal invariance. So here is just, let me see. Sorry, yeah, so here. So we assume, right, very simple matter, but only in this case, if this TABQ is proportional to HAB, we can preserve boundary conformal symmetry. And if you have some more general choice of TQ, it breaks boundary conformal invariance. So, but I mean, in general consumption, of course, we can put some any matter you like on this surface Q end of the world brane. But of course, as we can also do same thing for in the bulk, right? In the bulk also we can put, I mean, scalar field and so on in the bulk, but in the same way we can put matter field which localize on Q.
But is there some precise proposal in a specific context?
For that, we should look at some string theory, for example, embedding. And we have some simple example in the context of ADS4, BCFT2, that by using some ABGM theory. In ABGM theory, we can realize in string theory realization, of course, and we can introduce some type 2A, lives on type 2A string theory in ADS4 cross CP3. And in that case, we can introduce O8 plane, 8-dimensional orient fold. And that case, yeah, I mean, you have many matter fields in the bulk, actually. And you can put some brane, right? Also, orange fold plane, O8 plane, we can also combine it with D8 plane. D8 plane is necessary for tadpole cancellation. And we can put some D8 plane, and the D8 plane have a own gauge field, right? Super Amuse theory. And exact example of your matter field on brane cube.
Okay, thank you. I have actually another short question. So we know that there is some first law of entanglement entropy.
Yes.
So there is, if you excite your state a little bit, you had this. So is there, in the presence of boundary, can there be such a first law, and one can test this proposal better? This.
Good. Yeah, I think but it's very similar, because the first law, first law basically come from near ADS region. And we're talking about some region, sub-region A, right? And we are talking about contribution near boundary. So that part, I think, essentially same as case without end of the world brane.
No, if there is ending on this other brane, I was thinking whether we can test somehow this double minimization procedure in a much stringent way. Suppose you could place some boundaries and could test the first law about whether this double minimization is working.
Yeah, okay. Yeah, for double, the coordination to holography, maybe that's quite important actually. But for normal ADS BCFT, I think this, even though we have a double minimization, but this, I mean, end of the world brane part will not give some significant contribution to
right. Because it's not really the boundary.
Yeah.
Okay, I see.
But we have to maybe get it.
Thanks.
So Shubha has a question, please ask. Go ahead.
Yeah, so sorry, I might have missed a part of the beginning of the talk. So I'm curious, is this Branes distance, which is the quantum information metric you had, can it ever give time-like distances, or does it?
Okay. Yeah, of course, by definition, quantum information metric defined this way, Branes distance, it's positive definite, and there are no Lorentzian direction.
So there's no way to recover full ADS metric from this.
Yeah. So the idea is to use just Euclidean. We just reproduce Euclidean ADS metric.
Euclidean directions.
Yeah. We can actually put some time dependence in the end, right? Whole excited locations. W is the original Euclidean complex coordinate, but we can analytically continue, right? For Lorentzian time direction. And then, metric, we can also analytically continue this metric. Then we get the Lorentzian contribution.
I see, but that analytic continuation, is it unique or?
Essentially unique. I think that's unique. Yeah, because this is a very simple setup.
Okay, so is there some reference you can? Is there some work you can?
Basically you can look at this our paper. We discussed some this paper with Kusuki and Suzuki and Umemoto. There are only one paper with this author, and that we discuss also time dependence.
Okay, I will look at that. Thank you.
Shouvik, you have a question now.
Hi, Tadashi.
Hi.
So you had this transition between the minimal surface and the island, and that happened at some value of kappa, which was 3 minus 2 square root.
Oh yeah, so right. Yeah.
Can you explain why is that value special?
This value, okay. This value basically, competition between connected one and disconnected one. So this is basically, this is related to this cylinder geometry, right? This annulus geometry. And we are talking about the distance between this horizontal separation and this periodicity of the circle, and which is larger. This is very similar to the second Rényi, the second Rényi calculation on torus, actually. So we are talking this, we have a moduli, right? In cylinder, we have a moduli, and vertical distance and the horizontal distance. And we take a ratio. And if this ratio is greater than 1, then this geometry is favor. And it's opposite, then the other guy favor.
Okay.
So it's a kind of just fixed by moduli. Yeah, this kappa is just come from this simple, moduli.
Okay, thanks.
Any more questions? If others not have question, may I ask a question actually? So when you show the pseudo entropy part, so you said that because you are considering a time dependent, means Euclidean time dependent background. What is the precise prescription? Is it same thing like this covariant entropy prescription, the computing?
Yeah, actually, but in covariant case, it's a Lorentzian space-time. So we cannot minimize area.
Okay.
We have to extend. But here, it's everything is Euclidean, and minimal surface is well defined.
Oh, I see.
Yeah. So it's very simple. It's just so we know like some for Euclidean setup, but static Euclidean setup. Just we take a minimal area, and this is just static version of holographic entanglement entropy. And here we just ask some time-dependent version of that.
So you don't put the t equal to constant in the while you minimize.
No. Yeah. So this, good point. Yeah, this surface is no longer on the t equals 0 time size. Sorry, this picture is literally maybe misleading, but this actually go non-trivial deviates from tau equals 0 surface. Because anyway, bulk is also time-dependent. There are no natural choice of tau equals 0 surface.
So you still minimize the theta, the expansion of this geodesic, like you do in the
we just minimize the length, geodesic distance or surface area.
But time dependent. I see.
Yeah, time dependent.
And also one more thing probably. So you have mentioned this connection with the boundary. So can you actually explain that one more time?
Sorry, boundary?
Sorry, the island. Sorry.
Island. I mean, this is ADS BCFT?
Yes.
Yeah, we calculate the entanglement. This is a basic formula of holographic entanglement entropy in ADS BCFT. And that already we need to include the island. Because the minimal surface can end on the boundary of surface Q.
So this is the boundary of the entanglement. This is the wedge, right? This So this inside this region is an entanglement wedge. Oh, I see. That portion you are saying it's like the island.
Right. Yeah. Yeah, actually, this is also used in this, for example, especially Arumeheri and Mahanjan and Maldacena and Zhao. But here we wanted to confirm this island prescription in ADS BCFT by just purely from conformal field theory calculation. Because that is not done. Actually, this is kind of, we proposed this, but it's just proposal, basically. In this 2011, we worked on this, but that's a kind of proposal. We wanted to confirm in precise calculation of CFT. And that's, half of my talk.
So, any more questions? So, if not, we thanks Tadashi again for the wonderful talk. So,
thank you very much. Okay, so let me stop my sharing.
I think we can move to the next talk after Tadashi's sharing. Hi, Costas, can you share the screen?
Yes, can you hear me? Hello, can you hear me?
Yeah, I can hear you.
Yeah, so I'm trying to share. Can you see my slides?
Yes. Can you move just a little bit, go one next page, just to check.
Sorry, move what?
I mean, change the page, just to check that.
Change the page, yes.
It's what.
Okay, should I start?
No, maybe let's wait for 3 minutes. So it's supposed to be.
Okay, sure.
Hi, Costas. How are you?
Hi, Sunil. Good. How are you?
I'm good, thanks. How are things in France? You are in Paris, right?
Yes, I am. We have curfew here, but not yet confinement. It's some kind of Coulomb phase. How about you?
Nothing really. I mean, we are supposed to be careful, but pretty much everything is functioning. We can go anywhere we like.
Do you have to wear masks or?
Yeah, we have to wear masks. Not that everyone, this is India, so everyone doesn't do that. But in principle, we do have to. But yeah. Our curve has declined steadily in the last month, which is amazing, but both in Pune city and in the country.
Really?
This doesn't rule out a second wave or third wave or anything else, but
why did it decline? That's because of measures, or it's spontaneous?
It's not clear. As usual, people are fighting over the answer to that question. My perception is that people didn't follow any measures particularly, so that doesn't seem like a very good explanation.
So that's an optimistic note.
That's optimistic because if we got this without following measures, then actually it should not come back up. Other people say it's because of measures. Some measures were obviously followed. For example, in my institute, they're following measures very carefully, but about what is an institute in the larger scheme of things. I mean, I would say that 80 or 90% of people are, barely following some very basic measures and nothing more than that.
I sorry to interrupt. Actually.
Yeah, please.
Maybe we could start.
Oh, you want to start? Okay, go ahead.
Yeah. So, so let's start our second talk. So we have Costas Bachas from ENS Paris, and he will talk about microscopic Planck branes and massive gravity. So hand it over to Costas. Please start.
Thank you very much. And let me start also by thanking the organizers for this wonderful meeting. It's very comforting in these unsettling times to wake up and look forward to some stimulating talks. So this has been a good week. I enjoyed it very much. And also my best wishes to David Gross, who is being honored. Jan said that this is a family meeting. There were children, grandchildren, great-grandchildren. I'm sort of a younger cousin, I guess, of David's. So I also wish him all the best. Now, the title of my talk, in a sense, will hook up very nicely to the previous lecture by Tadashi. It's microscopic Planck branes and massive gravity. It could have also been how do you couple holographic universes weakly? Now, this may sound a little mysterious to you, but you will see that it is not very far from the lecture we just heard about. But let me start slowly. So let's see. Yeah. So let me remind you, or if you are too young, tell you that about 20 years ago, the Randall-Sundrum papers made some kind of paradigm shift. They made a very intriguing proposal. In a nutshell, they said, do we live in a 5-dimensional anti-de Sitter universe? Actually, not in the bulk of it, but on a 4-dimensional Planck brane, localized in a codimension 1 brane. And of course, gravity would have dimensional. Now, it's amazing that these two papers have more than 15,000 citations. Actually, it's more than some of the founding papers of the Standard Model. And yet, I think its grounding in string theory is not yet firm. Somehow, for the older ones among us, string theory still is the sanity check of ideas about quantum gravity. And this particular idea, for reasons I will explain, is not totally firmly grounded in string theory. Now, soon after the Randall-Sundrum papers, Karhan Randall explained indeed that the right holographic dual, the way to view this thing, is that of boundary conformal field theory. And the Tadashi explained also this very nicely, and Shira will talk about this later also today. So the basic picture is the one you just saw in the previous lecture. You have, say, ADS5 here. I will stay 4-dimensional for the brain. Bulk is ADS5. There is the boundary of ADS5 is the blue line you see here. And the brane, the end of the world or Planck brane, typically has some ADS4 geometry, at least in the simplest case. And there is a locally localized and massive, as a result, graviton that lives here. And this was part of the Karp-Randall twist of Randall syndrome. Now there is, since then, there is an extensive literature on holographic BCFT and the close cousins of it, which are interface CFT and defect CFT. And there is a lot of applications to condensed matter theory. This is not what will interest me today. Here I will be interested on the quantum gravity side. And in a sense, there are three different motivations that to study this problem. One, and the older one, is that this, as I said, is a real change of paradigm for string vacuum compactification. And the question is whether we should take it seriously or not. And closely related is the fact that there is a whole community of people that have been working on massive gravity theories in the last 20 years, actually going all the way back to Pauli and Firth. And one may ask in a related manner, is this really part of the landscape or is it in swampland? Finally, and this was mentioned in the previous lecture, the recent models of Page curve with entanglement islands that started with these very stimulating works make a use of this Planck brane in a non-trivial way. So this is a more recent motivation to try to understand this problem more precisely. So here I'll start somewhat unconventionally from point 2, but as you will see, all three are closely interrelated. So here's the plan of the talk. I'll first start, as I said, from a rather orthogonal point of view, which is massive and bimetric gravity in ADS. I will describe the holographic duals and a little bit about supersymmetry, which allows us to keep technical control, as you know, always in string theory. Then I will go to the microscopic embedding of the simplest, maybe, models that we have, the dual geometries, and the main technical result, as you will see, will be a mass formula for the graviton and the related breakdown of effective field theory. Then I will finish with some comments. So let me start rather unconventional in a sense by thinking about two universes. The two universes will be eventually ADS plus small perturbations. And I want to couple them via some kind of local interaction. Now, before coupling them, the two universes have two separate Einstein actions, different cosmological constants, maybe different energy momentum content, so matter fields. And of course, they live on different manifolds. So I use small x, lowercase x, and capital X for the coordinates of the two manifolds, and lower g and capital G for the metrics on them. So as long as these are separate, that's very dull. But the question is, how do you make them interact? And to make them interact, well, there are no-go statements. You cannot use two derivative couplings, but you can use mass deformations. And if you think a little about it, the way to write down any sort of mass deformation that preserves the separate diffeomorphism invariances of the manifolds is to have, of course, a mapping, an embedding of manifold capital X to manifold little x. So this embedding is given by these four functions, xm of x mu. And if you give me this embedding, I can pull back the metric capital G to the other manifold, and then it's easy to write down invariant couplings. So this is the generic form of the bimetric theories. You have to somehow think now about this interaction term. And before saying a little more, let me say that this story has also a long history. I mean, the first question is whether such effective classical field theories are at all consistent. This starts with Firth and Pauli. Much later, Isham, Salam, and Stradi, who wanted basically to couple spin 2 mesons, ordinary mesons, to gravity, thought again about reinstituting double diffeomorphism invariance. And maybe the paper that started the modern interest in this way of thinking was the Arkani Hamed George I. Schwartz paper in 2002. But since then, there is a very large literature. And the basic classical problem is very simple to understand. We have 2 gravitons. When these are massless, this each has 2 independent polarizations. But when they mix, one of them will become massive. So this is 2 + 3 = 5 spin states. On the other hand, I have just introduced, without telling you, 4 Stuckelberg fields. These are simply the coordinate mapping from one manifold to the other. Now, these are 3 + 1, 4 fields. They are scalars if you view them from the point of view of the little x manifold. But clearly, we only need 3 degrees of freedom. The 4th one actually turns out to be a ghost. It's called Bulwer-Desser. And somehow consistency tells us that it should decouple. So unlike spontaneously broken young Mills, where if you play the same game, the classical theory is fine, it's the Higgs with infinite Higgs mass. Here, even the classical theory is problematic. Now, there is a huge literature. There is a whole community that has thought about the problem. And there was a nice progress 10 years ago by Deram, Gabadadze, and Tolley, who managed to write down a 3-parameter interaction Lagrangian in which the ghost drops out, classically at least, and for identical backgrounds, say both ADS. Now, if you manage to do this, this is a bimetric theory, as I said. However, it is very simple to freeze one of the metrics. Just take one of the Planck scales to infinity. The 2 Planck scales are independent. This freezes the fluctuation of capital G mu mu, GMN. GMN becomes now an auxiliary frozen metric. And this is what usually people call massive gravity. So now one of the gravitons, actually the massless one, decouples, and only the massive one is left behind. That's all very nice. Now, there's also one final thing one can see, namely, you can just look at the Stuckelberg fields Xm of x. They enter in this Lagrangian, whose form, as I told you, a priori could be generic or could be of the DRGT form. And now you can ask the question, when does this field become strongly coupled? This is a nonlinear Lagrangian. The field becomes strongly coupled at some point. And this strong coupling scale is known as λ3 in this community or literature. And it's a very simple classical argument. It's a power counting argument. This λ3, you see, is some kind of geometric mean of the Planck scale and the graviton mass. Actually, it's the square of the graviton mass times the Planck scale to the power 1/3. And this means that there is no smooth limit. If you try to take the mass of the graviton to 0, the whole effective theory breaks down, essentially, because this λ3 collapses on U to 0. Now, this can be checked also by just doing 2-to-2 scattering and checking unitarity. And there are several recent papers, some of them are here. And basically, they all tend to say that there is evidence that any sort of spin less than 2 fields will not help alleviate the problem, cannot push the validity of these effective theories higher than λ3. One final thing I want to mention here is that this λ3 scale I showed here is actually the one around Minkowski space-time. It's easy to do also the power counting argument around ADS. The net result is that 1 power of the graviton mass is now replaced by the ADS horizon radius scale. So it's almost the same thing as of ADS, the whole thing to the 1/3. Now, here I will have to say a little more because effective field theory and 2-to-2 scattering doesn't have the same meaning as before. What does it really mean to say that this is the range in which effective field theory can be trusted? So the way I will interpret this is by saying that in a sense lambda 3 prime is the threshold for new spin 2 operators in the dual conformal theory, and that if you could do conformal bootstrap as opposed to 2-to-2 scattering, you would see exactly the same thing, namely that if you put a small mass or anomalous dimension to your leading spin 2 operator, you would need a whole tower of them to condense. But this is in a sense a hypothesis which has not, as far as I know, yet been checked. Okay, now, before I go to holographic duals, are there any questions on this? Okay, now, what is the holographic dual of this? And actually, this was used in 2 nice papers by Ilias Kiritsis and also Aharoni, Clark, and Karch, who asked the following orthogonal question. They said, well, 2 ADS universes are 2 conformal field theories. Let's call them lowercase CFT and capital CFT. Now, we want to put them together. And of course, the simplest thing to do is to write down some coupling, which is a double trace coupling. You take one operator from one theory, the other from the other theory, you couple them together. If you make sure that the dimensions are 3, here the CFTs are 3-dimensional because the dual theory is 4-dimensional. So if these dimensions add up to 3, then lambda is marginal, or at least marginally relevant or irrelevant, and therefore it can be made very small. And the question is, well, here is how you would couple these 2 holographic universes together. And indeed, it's very simple to see that we are talking exactly about the same thing. Before coupling the universes, each CFT has a separately conserved energy momentum tensor, T, lowercase t, capital T. Now, when you couple them together, the total energy momentum tensor, sorry, I changed IJ to AB here, it's the same object. So the total energy momentum tensor is still conserved. So a conserved energy momentum tensor has scaling dimension 3. And if you use the dictionary of ADS-CFT, which tells you that delta delta minus 3 is the mass squared in units of ADS radius, this means that that's a massless graviton. So the total energy momentum tensor is massless, is conserved. The relative one, on the other hand, needs not be conserved. There is exchange of energy, so it can pick up an anomalous scaling dimension, epsilon g. And epsilon g is essentially the mass of the second spin 2 primary operator. Now, I have used here combinations which are normalized so that the 2-point functions are 1, and so that the relative t is actually a primary field of the total t. And to do this, I needed the central charges of the 2 theories. The central charges simply enter in the 2-point function of the canonically normalized energy momentum tensors. So I call them little c and capital C. And you can easily check that these are normalized to 1 and that they are orthogonal spin 2 operators. Okay, so this anomalous dimension will be the key player in what follows. And now the limit of massive gravity, this is still bimetric theory, but the limit of massive gravity is very simple. Just take capital C to infinity. You can easily see that this operator formally goes to 0, and this operator, the relative one, formally goes to t, small t AB over square root little c, which is precisely the normalized operator of this theory. So in a sense, the energy momentum of this theory is now leaking into some huge other thermostat, if you want. It's not a thermostat, it's some coupled huge theory. And therefore this leaking, provided it's weak, is what gives an anomalous dimension to the energy momentum tensor. Actually, Aharoni et al. Went a step further and computed in conformal perturbation theory, leading order, this anomalous dimension. And it has a very simple form. It's some number, not important for us, lambda squared, the marginal coupling, times 1 over little c plus 1 over capital C. So you see the anomalous dimension is small, either if the coupling is weak, that's normal, or if the central charge of the theory, so I'm going now to massive gravity, this goes to 0 because capital C goes to infinity. If little c is large, if my CFT is large, in a sense, this also suppresses the anomalous dimension. It looks superficially like a one loop quantum gravity computation. And actually Porati, who wrote some very similar ideas a little before, just used transparent boundary conditions and the one loop calculation to get essentially the same answer. Now, there is a serious limitation, although these are very interesting, there is a serious limitation. Double trace, as you know, is very dangerous. First of all, well, it corresponds to an alternative quantization in gravity or transparent boundary conditions. However, it doesn't have really a geometric meaning. It's some kind of two-particle condensate, and definitely it has no known string theory embedding. And here I want a real string theory setup. So even though this is very interesting, it doesn't quite do the job. So with Ioannis Lavdas, who was my student, he's now a postdoc in Munich, we basically proposed to overcome this limitation in the following very simple manner. Rather than couple via a double trace operator the theories, why not just put a gauge mediator? Now, the precise context, as you will see, is that the CFTs I'm talking about are linear quiver Gayotto-Witten theories. I will say a little more about this. And what you do basically is gauge a common global symmetry. This ties them up together. And now, if these mediators, which will be some kind of U little n gauge theory, are massless, you cannot simply integrate them out and replace them by a double trace coupling. So we are definitely not in the situation of the previous setup. It's a different, if you want, mechanism. And as you will see, this will allow us to actually embed this precisely in string theory. Now, for this to work, I need, of course, to have a geometric setup. I need all the gauge groups to be large. This means that little n squared would have to be large compared to 1, but it has to be very small compared to the central charges of the two CFTs at the two ends. This will allow us to have both a semi-classical geometry and very weak exchange of energy momentum between the two. Okay, before showing you more precisely the geometry, let me make a few comments about supersymmetry. Now, what I said up to here doesn't use supersymmetry. Now we need supersymmetry if we want to have control. And it turns out that some very simple representation theory leads to rather stringent algebraic constraints on when you are allowed to do what I just described. So these are, if you want, algebraic constraints for massive supergravity or for defect superconformal field theories, which are in a sense analogous to Nam's famous classification of superconformal field theories. In a nutshell, the reason you get these constraints is the following. First of all, the way that a spin 2 multiplet becomes massive in the language of representation theory is that whereas it was a short multiplet, it had null states due to the conservation of energy momentum, it has to combine with something to become long. The something is the Stuckelberg fields, and there are cases in which this simply is not allowed by supersymmetry. In this case, massive supergravity cannot exist. The second constraint is that if you want to do a double trace coupling, you need to have relevant or marginal operators, which are top components of supermultiplets in tensor products. And this is again limited. So it's a straightforward thing to try to see what this tells you. And here, let me say very little about representation theory. So this will be quick, but essentially, if we stay with 4 dimensions, the conformal group is SO2,3. A unitary highest weight representation of this is described by spin and scaling dimension, S and delta. And unitarity tells you that delta has to be bigger than the threshold, which is S+1, at least for spins higher or equal to 1. So now the breaking of a global CFT symmetry, which is the Higgsing of the dual bulk gauge symmetry, corresponds to basically breaking the conservation law of the corresponding current. So here, that's the energy momentum tensor. You need something on the other side, a non-vanishing operator. This is the Stuckelberg field, which becomes null at unitarity threshold. But away from the threshold, you just have, in terms of representations, that a massless spin 2 and the massive vector becomes basically a massive spin 2. A short plus Stuckelberg becomes a long representation. So this is quite standard. But now we have to do it in the presence of supersymmetry. And in particular, in 4 dimensions, the supergroup is OSP4N, and you have to say under what conditions what I just said can happen. And now there are 2 things that can happen here. A, things can work exactly as without supersymmetry. So the short multiplets are at the edge of a continuum of long multiplets, and then things go as before. But there are situations in which the short multiplets are absolutely protected. They are separated from the continuum of long spin 2 multiplets by a gap. And in this case, parametrically small symmetry breaking is forbidden, and those cases are excluded. So it's very simple to find no-goes here. And there's a very nice scan or compendium of all unitary highest weight representations in more than 2 dimensions by Cordova, Dumitrescu, and Interligator, based on a lot of previous work, of course. And if you use this criterion I told you before, well, for the case of 1, namely what kind of short spin 2 representations can become long, the result is not at all surprising. You find that the conformal theory has to have dimension less than 4. So this cannot happen for ADS6 or ADS7. And you find that the supersymmetry has to be less or equal to half maximal. And this corresponds precisely to all the non-superconformal boundary or defect CFTs. So for instance, there are no codimension 1 CFTs of 6-dimensional to 0. This is simply not allowed by representation theory. So it's not surprising, but it's still nice to see that what we expect is in a sense proven by this very simple argument. All the known superconformal defects that we know fit into this classification. Now, to think about double trace, you have to do a little more work. You have to look in this paper of mine of last year. In the end of the day, here is the table that summarizes everything. So in a sense, the most supersymmetric situations that are allowed is massive ADS4 and ADS5 supergravity with half maximal supersymmetry. Don't worry about these. These are the representations in the Dumitrescu et al. Convention of the graviton and the Stuckelberg. The comment I want to make is that both of these maximal SUSY massive gravities cannot work with multi-trace deformations. Only with this gauge mediation process can they work. So that's one more reason why gauge mediation is in a sense superior. There is also an intriguing remark for the cognoscenti, which is that the massive half maximal graviton multiplet has exactly the same content as the massless maximal supergraviton. So for instance, one may wonder whether n=8 supergravity in 4 dimensions can have a phase in which you get massive n=4 in ADS. I want to say something more about this. We work on this with Severin List. Good, now I will go now to string theory and to the microscopic embedding. And now the original actually Randall-Karch proposal for the end of the world brane was simply a D5 brane wrapping ADS4 x S2 inside ADS5 x S5. Now this doesn't work, as you will see, but now we know much, much better about what can work. So ADS5 x S5 is n=4 super Young Mills. That's by definition, par excellence, you know, the place we want to be. And we are talking about end of the world branes here. And Guyot and Witten gave a very complete classification of half BPS boundary conditions for n=4, d=4 super Young Mills. They are basically, in string theory language, intersections of D5s, NS5s, and D3s. And in gauge theory language, they are simply linear quiver gauge theories. I won't say much about this. That's basically gauge theories with fundamental and bifundamental matter and with half maximal supersymmetry. Not only we know the field theory side, but we know very precisely the geometric side here. And the dual geometries of all infrared fixed points of these gauge theories have been now explicitly worked out. So the local form was actually worked out in a very nice set of papers by Docker, Estes, and Goodpearl. And the global constraints and the relation also to BCFT was worked out in these papers a little later by 2 groups. So we know practically everything in this case, and therefore you want to use it, obviously, to ask this question. Now, just a little more, Guyot-Witten described, as I said, these half BPS boundary conditions. Now, for us, the dominant actor is not the n=4, d=4 super Young Mills, but the boundary. It's the boundary, not the bulk. So it has to be large, as you will see. Its central charge has to dominate over the boundary. So it must have an independent existence as a very large 3-dimensional SCFT. And these SCFTs are called T rho sigma of UN, never mind. They are basically the good quivers of Guyot-Witten. The dual ADS geometries turn out to be exactly in one-to-one correspondence with the good theories, which is a very nice check of the duality. So you don't get the bad or the ugly theories on the dual side. You only get the good ones automatically. And this comes from a very detailed comparison of the data of this Young tableau charge data that you can find in this paper of Assel, myself, Estes, and Gomis. Here I will use only some very gross features of this well-studied duality. And first, let me tell you about the possible topologies of this duality. And here you will connect immediately with the previous talk. I will show you the 3 thin brain cartoons of them, which were sort of what Tadashi showed also. Well, one of them, which you may call interface CFT, is simply a brane that relates 2 different ADS5 bulks. So this is, a 3-dimensional theory that couples on both sides to 2 different n=4, d=4 super Young Mills. Now, if one of them is absent, that's BCFT. This is now simply end of the world brane with only a bulk on one side. But of course, you can also put two end of the world branes. And this you will recognize now the wedge of the previous talk. So I have 2 branes. The boundary of ADS5 in the dotted circle is now absent. It's thrown away. And the interior is ADS5. And now I say I will focus on this now in a minute, but when I said this is a cartoon, it's a cartoon because I'm pretending these are infinitely thin branes. And this is not really how the thing works, actually. But this anyway cartoon will now exactly match with the bimetric theory I just discussed. So here's how this works. So the thin brane is a bit misleading, but not completely. The full 10-dimensional geometry is essentially an ADS4 cross S2 cross S2 fiber. The S2s are there because of R symmetry, and the whole thing is fibered over a Riemann surface, a base. And the Riemann surface is a disk for linear quivers, and the fiber degenerates in various places on the boundary of the disk, and the places have charges of either NS5 branes in blue or D5 branes in red, or asymptotic semi-infinite D3s, which are precisely the ADS5 cross S5 bulks. But you can also truncate this away by formally taking these D3 brane charges to 0. Now, the solutions that are of interest for what I'm trying to get to, namely two weakly coupled CFTs, two heavy end-of-the-world branes, if you want, communicating through a small bulk, correspond to simply pinching the Riemann surface so as to separate two groups of singularities. So the picture is here. So you are pinching the disk. Then you can think of this as one end of the world brane. The other one is the other end of the world brane. And the middle is ADS5 cross S5, or as I will say in a minute, more precisely, Janus throat. Janus means essentially in this previous picture that the dilaton varies from one end to the other across ADS5. So this is essentially now the thick brane correspondence of this thin brane wedge. And if you want, it's the real story in string theory. And actually, because we know the mapping very precisely with Guyotto-Witten theories, you can work out, and this you can find in my papers with Lavdas, that this is precisely dual to the picture I showed you in the beginning. So you have two very big linear quivers. They interact in the bulk with a three-dimensional UN gauge theory. There's never a four-dimensional theory here. This is simply, there's no conformal boundary of ADS5. The conformal boundary is just ADS4. Again, if you go to this picture, you see it. The conformal boundary is S2 times R. It's not S3 times R. So the mediator is a three-dimensional gauge theory, and yet the dual geometry develops this very large region that resembles the ADS5 times S5 or Janus throat. And this is a very precise mapping. The geometry is exactly known and so on. So the Janus throat is now cut off on both sides at some large ADS4 radii, the fiber ADS4. So the radii, both on right and left, are much bigger than the radius of the throat, and the dilatons go to fixed values on the two sides. It is important, however, to stress here that the end-of-the-world branes are very large ADS4 flux vacua. They are not thin branes. The size of the compact manifold is of the same size as ADS4 radius. That's the same no-scale separation or ADS Swampland conjecture we heard about 2 days ago. It's the same reason. So in a sense, the real picture is that you have two very large, almost 10-dimensional universes connected by a very thin D3 brane throat, which has both an entry and an exit on the two universes. So in a sense, localized 4D gravity isn't really the correct word here. And we need to redefine what we mean, including in the title of my talk. Well, here is what I mean. There is still a sense in which we can talk about it. And as I said, the sense is that we have to think about the spectrum of spin 2 operators of this massive ADS gravity. And what I will call localized gravity, it's a misnomer, but that's what I really mean, is that if you look at the spectrum and you think about the anomalous scaling dimension of spin 2 operators, there is a distinguished light one whose scaling dimension is almost 0. It's separated by a gap with the following ones. And now the following ones, the continuum, can start either somewhere below 1 or the latest at 1, because at 1 you have both Kaluza-Klein and multi-trace spin 2 guys that come in. And because I have no scale separation, you know, these guys will be always there. Maybe not as a continuum, but as a very dense set. So what I mean now by massive gravity, keep in mind, is this, and hopefully this will connect to conformal bootstrap when we manage to correctly apply conformal bootstrap here. Now, I can still, though, use my effective field theory breakdown prediction. Remember, effective field theory predicted that the gap will shrink if I try to take epsilon to 0. You can convert lambda 3 to an anomalous dimension. I call it epsilon 3. And this epsilon 3 is this combination. It's the anomalous dimension of the lowest spin 2 times the central charge of the theory to the power 1/3. Now, our result, our main quantitative result in the paper with lambdas is that we actually calculated this epsilon g in the setup I just described. And you see the formula is very much reminiscent of the conformal perturbation theory formula. It's given here, but we have a very precise meaning for the lambda here. There is no conformal perturbation theory here, but lambda effective is this very specific combination of the rank of the mediating gauge group and the change in the dilaton across the Janus throat. So you see that there are two crucial parameters that enter in the scaling dimension. One is the rank n squared over c. This is the number of degrees of freedom of the mediator compared to the end of the world branes or universes, and delta phi, which is the variation of the dilaton. And if we take epsilon g as a measure of the leaking of energy momentum between the two, or of how weak the coupling of the two universes is, this can be made small either because the mediators are very scarce or because the two CFTs have very different dilatons. And this is a hidden parameter of the Gayotto-Witten theories, which is essentially something that measures magnetic to electric branes or symmetries, but I won't tell you more about it. You can look at the paper for the dictionary. Note also that the three-dimensional mediator has infinite gauge coupling. So the fact that the gauge coupling is infinite doesn't mean that the two universes couple strongly. I mean, epsilon is still arbitrarily small, can be made arbitrarily small. So now you can ask the question, what about breakdown of EFT? If I make EEG parametrically small, where is the new tower of spin 2s coming down from? Now, you can try to make this parameter arbitrarily small, but this doesn't work because n, the rank of the mediator, is quantized. And you can see that epsilon 3 is always bigger than 1, which anyways our breakdown Kaluza-Klein scale. But I can take delta phi to infinity, actually. This is essentially very similar to saying that you take a bulk 4-dimensional super Young-Mills, even though there isn't one. I mean, there would be one if I decouple one of the two end of the world branes, and I take each gauge coupling to 0, and this is effectively the same as that. So now, by doing this, I can indeed restore energy momentum conservation and take epsilon to 0. Again, fortunately, we know exactly the spectrum in this special Janus geometry. Actually, we had computed it with John Estes for different reasons, well, related reasons 10 years ago. And what happens is that when delta phi goes to infinity, ADS5 is deformed. It's deformed to ADS4 times an open interval of length, the variation of phi, times a deformed S5. Again, it's a very under control geometry. You can calculate the tower of non-BPS spin 2 modes, and those are precisely have anomalous dimensions or masses which condense when delta phi goes to infinity. So here is a numerical plot of them.
Hi, sorry to interrupt, actually. Probably just because of the time, actually.
I have about 2 more, I think, transparencies.
Okay, sure.
I'm done, yeah.
Sure. Thank
you. So in a sense, the picture, to recap, is the following. Massive gravity is a very big 3-dimensional CFT. It interacts, even take now the limit, as I told you, of decoupling one of the 2 end-of-the-world branes, but morally it interacts with n=4 super young Mills. The dual geometry is a big cup with a thin Janus throat that opens up on one side to ADS 5 versus 5. And this is the real holographic bridge between the 2. And what I tell you is that if you try to decouple the 2, there is a condensing tower of spin 2 modes. So the decoupling limit is a singular limit in geometry. So this brings me, essentially, I'm done, to 3 questions and remarks. First of all, Randall-Sundrum gravity has not yet found its place in the landscape or the swampland. The microscopic embedding via boundary super young Mills 4 gives really flat 10-dimensional caps rather than thin Planck branes. There is no space separation. So at least if you are interested in localizing gravity, you have to worry seriously about this question. Secondly, the anomalous scaling dimension of the lowest spin 2 measures, in a sense, the coupling of the 2 CFTs or the dual ADS universes. And the breakdown of the effective field theory is interpreted as a condensation of spin 2 modes in the decoupling limit. And amazingly, the geometric bridge knows exactly about it. And one may then ask, is this true for all cases of weak coupling, including double trace? Should the limit be singular? And should we see some condensing tower, since the effective field theory argument doesn't care about how you couple the 2 universes? And I think only if integrability comes in can we probably really answer this question, because these are non-BPS observables. And finally, of course, one asks, how do these things transfer to all this very nice recent work of islands, models of page curve, and also cosmology? Especially Van Ramsdorff and collaborators have tried to connect to these microscopic branes. They have some nice original ideas, but I think there is a lot of work that should be done here. Thank you very much for your attention.
Thank Costas for a wonderful talk, and we can open the floor for the questions. I think Oyon again have a question. Oyon, can you ask?
Firstly, thanks Costas, and great to know that you are my uncle.
Yes, I am. Well, you're great. Maybe you're great. Grand uncle.
Great grand uncle, yes. And so about this condensing of these operators, this tower condensing. So is it correct to say that the throat will become only stringy and not the other 2 blobs?
No, nothing stringy here. So I'm in a situation where everything is geometric, smooth. And to get this, remember, I assumed that the radius of the throat is also very large compared to string scale. So this means that n squared, the n is the n of the mediating young Mills, and hoofed coupling and everything are always much bigger than 1. But the 3-dimensional cups have central charges which are even bigger. And this is what creates the hierarchy, which tells you that the cups are almost flat, or they have a very large, I mean, they dominate the physics compared to the bulk, right? If they didn't, then you would never have this weak leaking that you need to talk about end-of-the-world branes. I don't know if, maybe I can show you back here the key assumption somewhere here. Here, I mean, this thing in a box is important.
Okay.
So yeah, I'm in this regime. So everything is geometrical, and the non-BPS spin 2s I'm talking about are Kaluza-Klein modes bouncing back and forth between the two ends of the world branes. That's how you should think of them.
I see. But what happens exactly in this condensing limit that you said this throat will become singular or something?
So in the condensing limit, the throat becomes, so think of ADS5, you know, if you think about ADS5 in terms of ADS4 fibrations, the fiber has a scale which is something like cos hyperbolic of the extra distance x. So, you know, so basically at the bottom in the center of ADS5, you have an ADS4 fiber with very small scale, and as you go to the boundary, the scale or the radius grows to infinity. Now, when you go to the Janus deformation, the bottom of this throat becomes flat and extends. And when delta phi goes to infinity, it becomes an infinite ADS4 cross an interval, a direct product, not anymore a warped product. So in a sense, you separate completely the two ends of the world branes by some kind of plumbic fixture which becomes infinitely long. And that's where these extra spin 2s bounce back and forth.
Okay, thank you. Yes, thanks.
Olok have a question. Olok, please ask.
Yeah, hi. I had a question from the earlier part of the talk about this breakdown of the effective field theory at the scale that you showed. Yeah, this one, yeah. So here the ADS curvature is still greater than the graviton mass, right? In the problem.
The graviton mass is always much below 1 over L, if that's what you mean.
Right. So there, I thought that this VDVZ discontinuity was absent in the ADS, right? I mean,
absolutely. So there is no VDVZ discontinuity, but the breakdown I'm talking about is a different breakdown. You just look at the classical nonlinear Lagrangian of the Stuckelberg fields. You know, it's like thinking about the nonlinear sigma model in the usual Higgs breaking of gauge symmetry. And you are just asking, you know, when does this thing become strongly coupled? That's what this scale is about. It has nothing to do with VDVZ.
I see. Okay, thanks. Thank you.
Yeah.
So any more questions? Any more questions? Maybe I can ask one. Can you at the beginning you say there's like an interplay between this with the islands? Can you make some comments actually regarding that?
Well, the obvious comment, you know, Tadashi gave this very nice picture, right, of how the boundary, the thin brain BCFT interpretation gives you this end of the world where you go and attach extremal surfaces. And when these extremal surfaces attach there, then you get these islands. You know, the first obvious question to ask is what happens if this thin brain is not there? Because this thin brain is not really there. It's some very huge 10-dimensional space. So something different should happen. And I think it's a very nice, interesting question. And I don't have anything very sharp to say about it other than the fact that I think it's a very interesting question. Yeah.
We don't have any more questions. We can thank Costas again for wonderful talk. Thanks very much.
Thank you.
We can end this talk and move to the next one. So Shouvik can start sharing the screen.
Okay. Is it visible? And
it's visible. Can you change one slide, like just to check?
Okay. Yes.
So maybe we wait for 2 minutes.
Yes.
No. One minute. Okay, so let's start with the last talk of this session. So our third speaker is Shouvik Datta from CERN, and he will talk about 2D conformal blocks. So I hand it over to Shouvik. Start the talk.
Thank you, Arpan. So thank you to the organizers, Tanay, Ayon, and Suresh, for giving me this opportunity to present my work. And thank you everyone for joining. So I'll be talking about conformal blocks in 2 dimensions. And this talk is going to be based on 2 papers. One with Mert Beskin, who was a PhD student at UCLA and is now a postdoc at the University of Amsterdam, and Per Kraus from UCLA, and another paper with Diptar Kadas from IIT Kanpur and Madhusudan Raman, a postdoc at TIFR. So let me begin with some introduction and give some context as to what questions we are trying to address over here. So consider a 4-point function in conformal field theory. It's considered the 4-point function of 4 primary operators on the plane. And we can write this 4-point function. We can insert a complete set of states in between these 2 operators and write it as a sum in this manner. And in conformal field theory, we know that the states are organized into primaries and their descendants. And so we can reorganize this sum into a sum over irreducible representations, which are the primaries. And then you have a sum over conformal blocks, which contain the position dependence of where these operators are located, times these are weighted by the OP coefficients. Okay, so this is theory dependent information, whereas this is something which is universal. And in terms of equations, you can write this 4-point function in terms of the cross ratio without any loss of generality, and write it as a sum over conformal blocks in this manner. So I have in mind 2-dimensional CFTs, and each term in the sum holomorphically factorizes into the holomorphic dependence Z and the anti-holomorphic dependence Z bar. Okay, and so this is the decomposition, and in 2 dimensions we have Virasoro symmetry. And this Virasoro symmetry actually fixes the form of this conformal block. So that's the Virasoro algebra. However, unlike higher dimensions, where one can obtain the block in closed form, at least in even dimensions, but in 2 dimensions, this is a harder problem because you have an infinite dimensional symmetry, and the blocks are not known in closed form. So this is an example where the presence of additional symmetries does not make your problem easier, but in fact, it backfires and makes it a harder problem to solve. So it's worthwhile then to investigate these blocks from various regimes in parameter space. So these blocks depend on the cross ratio, the external dimensions of the operators, as well as the internal dimension. So it's good to explore, as well as the central charge. And so it's good to explore this block from various regimes of these parameters. So in this talk, I shall be telling you about 2 regimes. So the first is the semi-classical regime, where we have the central charge of the CFT to be large, as well as the individual operator dimensions of the internal as well as the external operators also to be large, with this double scaling limit that the ratio of the conformal dimensions divided by the central charge, this quantity being held fixed. Okay, so this is something which is called the semi-classical regime. And the other regime which we are going to explore is the regime of heavy exchanges, in which the intermediate conformal dimension is large, whereas all the other parameters are held fixed. So this is a regime of heavy exchanges. Okay, so the first regime is, which I'm going to explore, is the semi-classical regime. And there is a conjecture by Zamolodchikov from way back in 1987 that conformal blocks are expected to exponentiate at large central charge. So at large central charge, C going to infinity, as well as this operator dimensions being large with these parameters held fixed, the conformal block exponentiates and it takes this form over here. Okay. So this was conjectured quite a long time ago, and there has been various verifications of this via series expansions in the cross ratio, also from holography by obtaining this block from geodesic diagrams or Witten diagrams, and also by mapping the 2D conformal block to a problem in 4D gauge theory via these AGT correspondence. And it has always been seen to work. So there is compelling evidence for this conjecture, but a proof of this has not been seen directly. So how can one possibly prove this? So I'll tell you how this is proved. So that's what we did in this paper. So first I'll tell you the proof in words, and then I'm going to give you the technical details of what went into the proof. Okay, so the first step will involve writing the conformal block as an inner product of wave functions of some suitable wave functions in some suitable variables, which I'll be telling you about. And owing to conformal symmetry, these wave functions obey a constraint, which is given by a partial differential equation. And this partial differential equation obeys a WKB-like solution in the semi-classical regime. And once you have this WKB wave functions, you can evaluate now this inner product integral in order to obtain the conformal block. And you can evaluate this integral by doing a saddle point approximation. And once you do that, you can see the block exponentials. Okay, so that's the outline of how the proof works. This is now fully in terms of words, but now I'll give equations to what these sentences mean. Okay, so the tools which we are going to need is something which is called the oscillator formalism. So the Virasoro algebra is given by this commutation relation over here. And the Virasoro generators, which are the modes of the stress tensor, they admit a differential operator realization. Okay, so they can be written in terms of an infinite collection of these variables, and these are very much like the harmonic oscillator variables, but with different frequencies. So just like you have in the harmonic oscillator, the creation operator can be represented as C, and your annihilation operator is this derivative, and this commutation relation is obeyed. So it's over here is also similar. You have bilinear combinations of this creation and annihilation operators to give you this modes of the stress tensor. And this is, if you write it in terms of A and A dagger, I mean, this is similar to how you quantize the bosonic string, or in this specific case, I mean, it's how you quantize the linear dilaton theory, in which you can precisely get the modes of the stress tensor in terms of this creation annihilation operators. Okay, and one can also, oops, I'm sorry about that. Okay. Just
reshare probably.
Yeah, yes. Okay, about that. So we have the representation of the Virasoro generators in terms of these oscillators. We can also write down states in terms of these oscillators. So note that the conformal dimension of the irreducible representation or the primary appears over here, and one can build descendants, which are excitations on top of this primary by using these differential operators. And in fact, so the primary is represented by the number 1, and then you can write down descendants as various powers of these Z's. So just like, so the primary is this one, and then you can excite this primary by descendants by these creation operators in this way, and one can calculate the energy of the state, and it turns out to be the primary conformal dimension plus the descendant level given by the partition of the descendant level. Okay, and there's also an inner product for the wave functions. One can evaluate this in order to get various expectation values and evaluate the CAC matrix, for example, using this formalism, and things are appropriately normalized via this measure over here, so that one gets the right expectation values. Okay, so one can use this formalism in order to calculate conformal blocks. So how does one do that? So the Virasoro block can be written in terms of oscillator wave functions. So the way this works is that you have this Virasoro block, and it captures the contribution from one single Verma module. Okay, and so what you do over here is to you insert the complete set of states, which is the complete set of descendants corresponding to that Verma module. And then you do a sum over all possible descendants. So that's what this integral is, where this U and U bar are the in and out states for this descendants. Okay, and this is just a complete set of states insertion, and these two wave functions are given like this. And since these operators are primaries, one can trivially use the commutation relation of a primary operator with the Virasoro generator and get this relation. Okay, and then one can translate this differential equation translate this constraint into a differential equation. So this Virasoro generator acts on this U variable, so one can use the oscillator realization for this. And whereas this Virasoro generator acts on these primary operators, and one can use the standard commutation relation of a Virasoro generator with a primary operator, which is this. Okay, so this gives you a differential equation for this wave function. Okay, and one can write this out in detail, and this wave function, one can have a scale prefactor over here, and then you have the non-trivial dependence on the cross ratio as well as the oscillators sitting over here. And this is the differential equation which is obeyed. So it's a linear differential equation. And one now focuses in the semi-classical regime where one rescales these variables appearing over here. The details are not important, but the point is that in this regime, which is the semi-classical regime, this differential equation has a WKB solution over here, and once you plug in this WKB solution, this becomes a nonlinear equation in this way, and this can be shown to have a unique solution. Okay, and this S over here has got an expansion in terms of the cross ratio, which corresponds to a descendant level expansion, and each term in this expansion can be shown to be unique. So there is a unique solution. And once one has this WKB wave functions, these can be now used to evaluate the block, and the block can then be evaluated in the saddle point approximation in the semi-classical regime, and that directly shows exponentiation. Okay, so this conjecture now stands proved. So Virasoro blocks indeed do exponentiate in the semi-classical regime, and this can be non-perturbatively shown. And these techniques using oscillators are also useful in providing new derivations of some standard results in 2D conformal blocks. For example, the heavy, light block, the perturbatively heavy block, and the block with intermediate heavy exchange. So those results can also be recovered using the oscillator formalism. And furthermore, so this is a slightly different story, which I won't be talking about today. This oscillator formalism can also be very efficiently used in order to calculate matrix elements of primary probe operators in descendant states. So up to an overall OP coefficient, this is fixed by Virasoro symmetry again, and the oscillator formalism can be very efficiently used to calculate these matrix elements. And this can be used in order to test the eigenstate thermalization hypothesis, which is a statement about large diagonal matrix elements and small off-diagonal matrix elements. And these things can be tested in 2D CFTs, which was done by us in this paper. Okay, so I mentioned about the semi-classical blocks. So I'll move on to the heavy exchange regime. So this is the regime in which we have for external operators again. So their conformal dimensions will be held fixed. The central charge will also be held fixed, but the intermediate operator which is being exchanged, the conformal dimension of that is going to be heavy. Okay, and we are going to study this conformal block in the HP going to infinity regime, which is the conformal dimension of this operator OP being large, and we shall study this in the 1/HP expansion. Okay, so just a reminder about 4-point functions and conformal blocks. So we have this 4-point function on the plane, and crossing symmetry implies that f of c is equal to f of 1 minus z, and the conformal block decomposition in terms of the OP coefficients is this. Okay, and the Virasoro conformal blocks have quite an integrate form. They can be expressed in terms of the skew variable. So there is the structure which is there. So there are these 3 factors over here. This is completely known in terms of known functions, but there is this part over here which is not known in closed form and can only be determined recursively. Also, there is this Q variable appearing over here, which is very much like the Q variable that appears in torus partition functions. So this Q variable is related to the cross ratio via the elliptic K function in this way. And the inverse relation between the cross ratio and the Q variable is this. Okay, so note that under crossing, Z goes to 1/C. And if you use this relation, tau goes to -1/tau, which is just the S modular transformation, which clearly shows that there is something modular about crossing symmetry. So the modular features become manifest when we map the sphere with 4 marked points at which the operators are located to the pillow metric. So the pillow metric is given by an orbifold of the torus, and the explicit mapping is given by this, where X over here are the coordinates on the plane, and U over here are the coordinates on the pillow. And this is a normalization so that you have the lengths of the cycle to be 2 pi. So just like the torus, over here also, you have got 2 cycles. And how is this orbifold obtained? So you start with the torus. So you have a rectangle. If you identify the opposite edges, you get a torus. But before you identify the opposite edges, you fold it along the midway. And then you identify the opposite edges. And that gives you this pillow geometry, which has got 4 conical singularities and or 4 fixed points at which your external operators live. So this gives you the pillow geometry. And then crossing symmetry, which is Z going to 1/Z, which is going from the S channel to the T channel expansion, becomes equivalent to changing the cycles of the pillow. Okay, so you exchange the cycles over here. And while doing this map, while going from the sphere to the pillow geometry, one has to take proper care of the conformal anomaly factors, which was done in this paper. And after one does that, one can express the pillow correlator as a correlation function on the pillow geometry. And these states are has got these operators, and you insert a complete set of states, and so this becomes a trace. Okay, and what the conformal block is to, it takes the contribution from each Verma module in this trace. And one keeps into account the conformal anomaly factors from the last slide. And one has got this. And there are the extra contributions from the descendants, which is encoded in this quantity. Okay, so this part is known in closed form, but this can be determined via a recursive algorithm. So we know Q expansions for this quantity of this quantity due to some recursive algorithm by Smolachikov. So we will be investigating this block in the heavy exchange regime, where the intermediate exchange dimension is going to be large. So in order to make some sense of the structures that will be arising from that analysis, we need to remind ourselves about some modular ingredients. So the first thing is that the modular parameter tau takes values in the upper half of the complex plane. And one can go from these Cartesian coordinates to polar coordinates and map to the unit disk within a finite region, where this Q variable is e to the power 2 pi I tau. And another important concept, which is going to play an important role over here, is the Eisenstein series. So the Eisenstein series have a Q expansion given in terms of the Divisor functions in this way. And they can also be expressed in terms of lattice sums in this manner. And the good thing about these Eisenstein series is that these are modular forms of, so E4 and E6, these are modular forms of weight 4 and 6. And furthermore, they also generate a ring of modular forms of a given weight. So any higher weight modular forms can always be written in terms of a polynomial of E4 and E6. And also, we have got the second Eisenstein series, which is not modular. So it would have transformed as a modular form only if under modular transformation, this term was present, but instead you have an additional term, which is this. And the presence of this second term is called the modular anomaly. Okay, and these Eisenstein series are known non-perturbatively on the unit disk. So in these three plots, I've plotted the argument of these functions of E2, E4, and E6, and they look like this. Okay, so this is just a plot of the argument or the phases, and they look like this. Okay, so we're going to look at the 4-point block in the heavy exchange regime. So this part is already known, whereas this part is not known in closed form, but we are going to investigate that in the 1/HP expansion. So that's what we do over here. And we use Zamolodchikov's recursion in order to calculate this. And what we see is that each order in the 1/HP expansion can be written in terms of the Eisenstein series, its powers and its products, basically in terms of the polynomials of E2, E4, and E6. Okay, so each order is now known in closed form in terms of this Eisenstein series. Okay, and since the Eisenstein series are non-perturbatively known on the unit disk, one can just plot the conformal block in this regime and obtain this plot over here. Okay, so I was talking about 2D CFTs on the plane, but one can also study CFTs on higher genus Riemann surfaces. And the simplest case is that of the torus. And one of the well-known facts is that the torus partition function is modular invariant. So the next to simplest observables on the torus are one-point functions of primaries. So one can look at the usual trace with the usual Boltzmann factors, but with a primary insertion over here. And just like the primary is, just like the partition function is expanded in terms of characters, or the conformal, or the 4-point block is expanded in terms of Virasoro blocks, this 1-point function on the torus also admits an expansion in terms of the torus 1-point blocks. Okay. And one can also study these torus blocks in this heavy expansion, in this 1 over HP expansion, which is to say that the intermediate exchanged operator, the conformal dimension of that is large. So similar to the 4-point block, there is a known piece, like there's a prefactor which is known in closed form, but there is a part to it which is not known in closed form and which can be determined recursively, and there has been algorithms by these authors. And one can evaluate this, and once again in the 1 over HP expansion. And similarly, just like the 4-point conformal block, also for the torus block, what one sees is that each order in this 1 over HP expansion can be expressed in terms of polynomials of the Eisenstein series. Okay, and one can also check this to fairly high orders by numerically by using specific values of the internal as well as the external dimensions, and it works. However, the appearance of this E2, it signals a modular anomaly in the block, which I will come to. Okay, so one can also perform various checks. So there are some very special cases where the torus block is known in closed form. For example, at C is equal to 1 and H is equal to 4, it's known in closed form, and one can expand this in this 1 over HP expansion, and it shows perfect agreement with what we have over here. And one can also plot this just like the blocks on the plane, and one can plot its argument. And just plotting the first 3 orders shows no visible differences if you plot this one exactly. Okay, so what is happening? So it's not a priori expected that Eisenstein series should appear in conformal blocks. So where do these come from, and can we understand the structure over here? So what we have is that we have the 4-point block on the plane or on the sphere, and that has got this recursive part, and we have also got the torus 1-point block, and that has also got this recursive part, and we see that these parts over here admit a 1 over HP expansion, and each order in this 1 over HP expansion, we have polynomials of the Eisenstein series appearing. However, note that each order has got terms with different modular weights. So if you look at the second order, for example, so I'm just looking at the torus 1-point block for simplicity. So you have over here E2 square appearing, as well as you've got E2 appearing, which has got weight 2. E2 square will have weight 4. E4 has got weight 4. And so you have a mix of terms of various modular weights. Okay, so your first reaction is that, I mean, this is weird. This should not happen because we expect terms of uniform modular weight to appear at each order. So the next question you would like to ask is that whether a better reorganization is possible that restores good modular features at each order in this expansion. And indeed, the answer turns out to be yes. And that brings me to this Liouville parametrization. So instead of expanding the conformal block in the 1 over HP expansion, one can expand it in terms of the momentum of the vertex operators in Liouville theory. So in Liouville theory, you can parameterize your central charge in this way, and also parameterize your conformal dimension in this manner, where alpha is the momentum. And then what you can do is to take this H which is this, okay? You can take this H and take the log of this quantity. So this is, if this is like your partition function, you're looking at something like a free energy. And this has got a good expansion, and each order in this 1 over alpha expansion has got terms with uniform modular weight. So there is a constant piece, and there is a Q-dependent piece, and this Q-dependent piece is quasi-modular with weight G, with weight 2J at order J. So just to demonstrate this, So if you look at the torus block, now in this 1 over alpha expansion, so these are the constant pieces, but and these are the Q-dependent pieces in which you have at 1 over alpha square only E2 appearing. At 1 over alpha to the power 4, you have E4 and E2 squared. So these are now terms with the same modular weight. Okay, so we see that the momentum variable is better, and this is possibly because the S modular transformation for these blocks is implemented via this fusion kernel, which is actually neater in terms of the momentum variable. So we have this notion of a free energy in which we took the log of the recursive part of the block, and that had a good expansion in this 1 over alphas. And one can also look at the other channel, go from the S channel to the T channel, which is doing this S modular transformation. And that can be obtained via this fusion kernel action on the blocks. So the block in one channel can be written as a linear combination of blocks in the other channel via this fusion kernel. And using this fusion kernel, one can focus on the large intermediate exchange regime. And what one sees is that there is a saddle, this integral can be evaluated using a saddle point approximation. And there is a recursive structure for these edges. Okay, and so these edges have the Q dependence sitting over here. And the Q dependent piece, there is a recursion relation which comes about in the saddle point approximation. Okay, so this is what comes about, but this is something which is approximate and it is not perfectly obeyed, and it is desirable to have something which is exact. And in order to obtain the exact thing, I mean, a big import was done from this AGT correspondence, which is the correspondence that relates two-dimensional conformal blocks to 4-dimensional gauge theories. So there's a long story which starts with Nekrasov partition functions of 4D n is equal to 2 star super Yang-Mills theory. And this is related via this AGT correspondence to 2D conformal blocks. And using this, there is an exact recursion relation for each order in this 1 over alpha expansion, in this momentum expansion, which is this. Okay, so this relation can be explicitly checked from 2D CFT just by, we have the block expanded in 1 over HP, and one can check order by order that this recursion relation is obeyed. And we need two different seeds for the 4-point block or the spear block and a different seed for the torus block. Okay, so we have this recursion relation, but one can also build a generating function consisting out of these edges, which is where the Q dependence of the block is. And this is related to the block very simply via this exponential. And one can turn this recursion relation, resum it, and get a differential equation. So this is given by the Kardar-Parisi-Zhang equation, which appears in physics in a completely different context in the growth of surfaces. But we see over here, this differential equation also governs the block. So note that there is the E2 derivative over here. So this does not fix the block completely, but the purely E2 dependence of the block can be fixed via this Kardar-Parisi-Zhang equation. Okay, so, and this is keeping in spirit with Zvi's talk from the first day of this conference. It is going to higher orders and beyond, because this recursion relation gives you information about higher orders. And this differential equation is something which is non-perturbative. This gives you non-perturbative information about an object which is not known in closed form. Okay, so we have this recursion and we translated that into a differential equation which is non-perturbative. One can also write things slightly differently. I can write this f as log g and linearize this equation, and it simply becomes this diffusion equation, which is this. Okay, so to summarize so far, we have the conformal block. So there is a part to the conformal block which is not known in closed form. And we investigated that in this 1 over HP expansion. Then we took the log of that quantity. So we wrote it as a free energy. And we saw that the free energy has got a good expansion in terms of 1 over alpha, at which each order you have quasi-modular forms of a definite weight appearing. Okay, so these are given by polynomials of the Eisenstein series. So this is a recursive factor for the Virasoro block. And also we have this S-duality relation. So the block in one channel can be related to a sum over block in the other channel via this fusion kernel. And the E2 dependence of the block is captured via this diffusion equation, which is this. Okay, so so these are some new features which we see in the block. However, there is a function which is known and loved by string theorists, which is very simple, which is nothing but the Jacobi theta function, which is θ1. If you look at this equation, it is strikingly similar to what I showed in the previous slide. So if you write this, there is a representation of θ1. You can write it as an exponential, and which involves a sum over the Eisenstein series. So, and your z variable, which is this elliptic variable, is over here. So comparing with this, it's very similar. It is also an exponential of polynomials of the Eisenstein series, and you have a 1 over alpha expansion, whereas over here you have a z expansion. Okay, so you look at this and your first reaction might be that probably 1 over alpha is related to z. And you have the S-duality relation, which is nothing but the S modular transformation of this θ1. θ1 goes back to θ1. And so the fusion kernel over here is somewhat trivial, and it's given by the delta function. And furthermore, this θ1 is also a solution to the heat equation or the diffusion equation, which is a slightly different form to the equation which I showed in the previous slide, but it also obeys a diffusion equation of this form. So all of this makes you wonder that are the blocks some kind of generalized theta functions? So this is something to which we don't know an answer to, but we are currently exploring. But there are a lot of tantalizing similarities, but it might be possible to make some connection with weak Jacobi forms and this Virasoro blocks, but the relation is at present not very clear. Okay, and finally, these new structures, which are this Eisenstein series, also provides new constraints which can accelerate the computations of Virasoro blocks, and each order in this 1 by HP expansion is known in closed form, which is also a big advantage. So these blocks can also be used in order to derive formulas for averaged OP coefficients in the high energy regime, and these corrections in this 1 over HP expansion can be used to refine those formulas. So one question which we have not quite addressed over here is that why is the second Eisenstein series appearing? So it is not modular, but it is quasi-modular, which shows there is a modular anomaly in the block. So from 2D CFT, we don't quite understand what the origin of the modular anomaly is. So this is some work in progress, which we are trying to do. And clearly there are these loose ends to be tied. And so there's a lot more structure to be uncovered and something to be understood along these lines. So thanks for your attention.
Thanks, Shouvik, for the talk. And now we can take questions. So if you have any questions, please ask.
Hi, Shouvik. I wanted to ask you, this alpha played the role of Z in your theta function, right? Yeah, but alpha is real, right? Whereas, and
yeah,
is that right? And also,
right. I mean, it's like there are some similarities, but it's not like one can't make a direct connection because also your Z variable is periodic. I mean, whereas exactly, you don't approach
elliptic variable alpha, right?
Yeah.
So isn't it a natural way to complexify alpha in any way from your?
Yes, I think complexifying alpha would make sense actually. I mean, because if you look at the Liouville parameterization, it's actually purely imaginary. Just a moment, let me get to this slide. Yes. So yes. So alpha has to be purely imaginary.
Okay.
Okay. So if you focus on C greater than 1 theories, yeah, alpha has to be purely imaginary.
Nice.
Any more questions?
Shouvik,
Yes.
can I ask you about this ETH thing? So, is it what can you tell about? Is it what kind of large C CFTs will satisfy ETH? Does it? Do you have an answer to that?
Well, yeah. So okay. So yes, I mean this can be partially answered. I mean, if you look at OP coefficients, if you look at heavy light OP coefficients, so these should be the off-diagonal ones should be exponentially suppressed. I mean, if the OP coefficients are exponentially suppressed, the off-diagonal ones, and those are the CFTs which should satisfy ETH. So yeah. But that is not quite related to what I'm showing over here. So what I was showing here is something which is universal in the sense that you'll focus on a single Verma module, and then over there also you can look at matrix elements within that Verma module. Okay, so this is universal information which is fixed by symmetries. And what one can see is that if you have a light probe and external operators being heavy, so this is your conformal dimension of your probe and your external operators is heavy, then what you see is that the diagonal elements are much more pronounced compared to the off-diagonal elements. Well, this is something which one can explicitly work out and see.
Thanks. That's nice. But actually, I have then. Would you say that that holographic CFTs somehow will satisfy ETH or not? And there's no definite answer that comes out of this. Not a very sharp answer. Can you make a sharp statement about?
Yeah, the sharp statement would come from like giving details about the spectrum and OP coefficients. So you have to make some condition on the OP coefficients, right? And yeah, what I'm saying is that the OP coefficient should obey the ETH ansatz. Okay, yeah. So that I think should be true. Otherwise, it is not formalized. Yeah.
And about the off-diagonal elements, there's a stronger version of ETH, right? Can you test that too?
You mean that all states obey the ETH ansatz? That's what you're
saying?
No,
there's an off-diagonal. The diagonal. So there are these diagonal elements of the energy, or I think now the primaries, but you also have off diagonals. I think you have the off diagonals anyway. They should be suppressed. So you are stressing the stronger version anyway. I see.
Yes. Yeah, I was telling about the stronger version. Yeah.
Okay.
Those should eventually suppress by
right. Okay, thanks.
So on an average, this suppression can be seen, but the point is that this should be the suppression should be true at the level of individual OP coefficients. Only then the CFT is going to thermalize.
Right. Okay. Thanks. Yes. Thanks.
Yeah. So on an average, you can get these averages from modular bootstrap. I mean, yeah, in which these blocks play a role.
Any more questions? So, okay, if not, thanks Shouvik again for the talk. And, we can conclude the talk. Also, this concludes our this session, and we thank all three speakers, Tadashi, Costas, and Shouvik, for very engaging talks. And I hand it over to Arun.
Thanks, Arpon, for nicely conducting this session. And we will meet again then at 7:30 p.m.